Welcome to APEC. It's August 3rd, 2024, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody who's watching us on YouTube. This is a YouTube live stream, so we've got the whole gang there. And you guys can comment and use that chat tool to give us your feedback there. So today, Matti Pitkänen will present a topological geometrodynamics view of the Biefeld-Brown effect. Ryan Wood will discuss anti-gravity and UFO reverse engineering black projects. Alex Wolf III is going to talk about a comprehensive solution to the Reimann Hypothesis. Larry Deavenport will discuss his T.T. Brown FlameJet Generator replication. And our very own Gerald Papineau will present on EM coils and transverse gravitational waves. So again, I am super excited to have everybody here. A couple of quick notes, I guess. We are continuing our analysis of the ARTS parts sample. Again, this is a verified sample with a chain of custody. Mark Sokol just took that down and had some SEM analysis done on that. And again, that just further confirms because it matches past analysis that's been done. So that is really, really exciting. So that is going on. We have some other things in the works. I just completed a trip to Dr. James Woodward's lab. I met Jim. I got to spend some time with him and Curtis Horn. I got to see the work they were doing, and it is absolutely incredible. I had no idea that it had as much potential as it does. So this is very, very exciting stuff. So that is kind of current events, and we have some more coming up this summer that we'll keep you abreast of. Today's event is on StreamYard, broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed, please do so now. You can ask questions, again, using that live chat feature on the right-hand side of the page. We will do our best to go through those and ask them to the presenters depending on time constraints. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. So again, excited to have everybody here. I'm going to start things out with actually a pre-recorded video from Dr. Matti Pitkänen. He pre-recorded this because of bandwidth constraints. He is actually trying to get into the studio now. So while this is playing, we will help him. Do that. So let me hit the present button and share screen, and we'll see if this works. Yeah, perfect. Okay, fingers crossed.
TGD view of Biefeld-Brown effect. Biefeld-Brown effect is one of the effects studied by free energy researchers. What happens is that an asymmetric capacitor, for which the electrodes are of different size, starts to move in the direction of the smaller electrode. The so-called EM drive could be also based on this effect. Recently, I learned of the experiments carried out by Charles Bouler's team. An acceleration of 1g is achieved for a capacitor-like system in vacuum chamber, and the effect increases rapidly with the strength of the electric field between the electrodes. This raises the question whether new physics is involved, either as a failure of the momentum conservation or as a presence of an unidentified system to which a momentum transfer takes place. In this talk, I will consider a TGD-based model, in which the third system is identified as an electric field body associated with a system, or both electrodes. The key idea is that electronic momentum is pumped from the electrodes to the field bodies. An electron is transferred to the field body, leaves some of its momentum to field body, and robs back, and in this way gives rise to a recoil. For the smaller electrode, the quantum coherence is higher and the pumping is more effective. And this gives rise to the Biefeld-Brown effect, perhaps even in the situation when the dielectric is present. There is also a net transfer of electrons to the positive electrode. This reduces the voltage while keeping the system neutral and allows in this way to use electrostatic energy to kick the electrons to the field bodies. And this explains why the effect is stronger when the smaller electrode is positively charged. Biefeld-Brown effect and its modern variant. I will first discuss the experiment of Brown and then the experiments of Bowler. Consider first Biefeld-Brown effect. The electric fields associated with the capacitors which are asymmetric are about 30 kilovolts per decimeter. This is about 10% of the electric field, causing the electric breakdown in air. This electric field is about 1,000 times stronger than the Earth's electric field, which is therefore expected to not give any decisive contribution to the effect. The acceleration is in the direction of the smaller electrode. The effect is largest when the small electrode is positive. This might be understood if positive ionic currents are responsible for effect. The effect occurs in a dielectric medium, air. And Brown suggests that the effect indeed involves ionic motion. The effect can be used for vehicle propulsion or as a pump of the electric fluid. This is obvious. Center of mass acceleration is achieved. The detailed physics of the effect is not understood. There are two standard physics-based models for the effect: ionic wind model and ionic drift model. The center of mass motion should be due to the loss of energy, perhaps the loss of the electrostatic energy of capacitor system, and the momentum to the environment. Ionic wind involves no friction, and the prediction is 3 orders of magnitude too small. The effect is small since the absence of dissipation tends to reduce the effect, since the ions arriving to the opposite electrons should induce a compensating recoil. I must admit that I don't really understand that there is any effect at all. My understanding is very naive here. Then there is ionic drift mode. It predicts an order of magnitude which is consistent with the findings. The modeling of the situation in the dielectric reliably is, however, difficult. Consider now the findings of the group of Charles Bowler. Bowler's team has been developing the propellantless propulsion based on asymmetric capacitor-like systems. Understood in very general sense, the two electrodes can be very different from capacitor plates, but are asymmetric. The second electrode is smaller. The experimental arrangement looks like follows. Electric field is more intense at the smaller electrode, and this is believed to be responsible for the effect. In the experiments of Brown, the effect was larger when the smaller electrode was positively charged. I'm not sure about this. I would guess that it is so also now. The electrons are cased so that there is no leakage of charge between them. This prevents all kinds of leakage currents between the electrode and poses an additional challenge: how the charge can be transferred between the electrodes if the ordinary mechanisms are not possible. The system is enclosed in high vacuum, and this allows to use lower voltages. There are profound differences between the situation in the recent experiment and experiments of Brown. First of all, in standard physics, the center of mass of an isolated system must remain at rest, no acceleration. Now the system is in a vacuum chamber and there's no charge leakage between the electrodes. But there is center of mass acceleration. There should exist momentum and energy exchange with some unidentified system which we could call X. Charges and or radiation should leave the electrode to produce recoil. And recoils would not compensate for each other. This is highly non-trivial condition. The asymmetry of the system and also the transfer of momentum to this X could guarantee this. Mere charge and electric field are enough to generate a thrust. And there is no external electric field. The electrostatic energy should provide the needed energy. Two types of charges are involved. The free charge in conductors and the bound charge appearing in insulators. Bound charge could correspond to valence electrons which do not become conduction electrons in case of insulators. In this process they could become something new, perhaps associated with this unidentified system X. At low voltages, free charge dominates conduction electrons, and at higher voltages, bound charge dominates. The increase of the effect is dramatic. Okay, what could happen to the electrons? Without a transfer of electron momentum to the degrees of freedom of system X, the generation of the center of mass momentum is impossible. The electrons transferred to X end up to the opposite electrode or drop back to the original electrode. And in this process, pump momentum X to X. If some part of momentum is left there, it be either due to friction, ohmic losses, or it could go to the internal degrees of freedom. The asymmetry suggests that the pumping from the smaller electrode is more effective. Suppose that the electrons get their energy from the electrostatic energy of a capacitor-like system, and the net charge of the system remains zero, as looks natural. This requires that there is a net transfer of negative charge to the positive electrode to keep the net charge vanishing and to reduce the voltage. It is indeed easy to see that the accumulation of negative charge to X is not possible. It would generate compensating positive charge to a capacitor-like system. Therefore, the momentum of electrons must be decimated or transferred to some internal degrees of freedom of X. One can't exclude the possibility that some fraction of electrons remain to X for a relatively long time. The capacitor system would in this case experience a force in the electric field of Earth. System X plus capacitor type system would behave like an electric dipole in the electric field of Earth. Since the Earth is negatively charged, the force on capacitor-like system would tend to decrease the thrust. It would be directed towards Earth. Consider first the basic ideas of the TGD bed model of Biefeld-Brown effect. There are 4 key elements which I want to discuss briefly next. The first new key element is a new view of space-time and fields provided by topological geometrodynamics Geometric vision leads to a new view of space-time. Space-time would be a four-dimensional surface inserted in hyperspace, which is eight-dimensional. It is Minkowski space, the space-time of special relativity, with points replaced by CP2, complex projective space, which is four-dimensional. This implies that space-time is topologically non-trivial in all scales. I speak of many-seated space-time. The space-time surfaces have finite size and their boundaries correspond to the boundaries of physical objects. This is something very different from the view of general relativity. Space-time surfaces can be seen as orbits or particles, identified as free surfaces, which by four-dimensional general coordinate invariance must satisfy holography. They are analogous to Bohr orbits or particles. This has enormous implications for the theory, and the generalization of point-like particle to free surface brings in size and shape as dynamical degrees of freedom. The new view of classical fields is also brought by TGD. The classical fields associated with physical systems correspond to finite space-time regions, sheets. One can talk of field identity or field body, or about magnetic body, electric body, also gravitational field body. These field bodies have size and shape, and they have flux tubes and flux sheets as body parts. This is essential for the entire phenomenology of TGD in applications. Field body has as its body parts of flux tubes and also flux sheets. TGD predicts two kinds of magnetic flux tubes and also electric flux tubes. Monopole flux tubes have a closed cross-section. This is not possible in Minkowski space. And they are closed. This reflects Maxwell's equations, no free magnetic charges. Maxwellian half-monopole magnetic flux tubes are also possible. They have boundary. It could be disc-like shape, this cross-section. And they need not be closed. They would be these Maxwellian things. And could be important in the temperature region above the transition temperature in the case of high TC superconductors. In superconductivity, they would become monopole flux tubes. Monopole flux tubes are in a key role in the TGD-based quantum biology and also in cosmology and so on, superconductivity included. There are magnetic and electric flux tubes. Electric flux tubes are very near to magnetic flux tubes. They are obtained as a small deformation of the magnetic flux tubes, so that these monopole flux tubes would have also magnetic fields. And I already mentioned these two kinds of flux tubes, monopole flux tubes and the Maxwellian ones. The third important new ingredient is hierarchy of Planck constants. It labels the phases of ordinary matter behaving like dark matter and residing at field bodies. This dark matter is not galactic dark matter. It would be responsible for mysterious missing baryonic matter whose portion has been increasing during cosmology. And whereas galactic dark matter would be dark inertia in the TGD framework. This hierarchy of Planck constants is predicted by number theoretic vision of TGD, which is something totally new. In standard physics, one does not have number theoretic as a fundamental element. The larger the value of effective Planck constant is, the longer the quantum coherence lengths are. And field bodies can be macroscopic quantum systems for large enough values of effective Planck constant. The algebraic complexity also increases with this effective Planck constant. This is essentially the dimension of algebraic extension of rationals, characterizing the space-time region in question. When you have polynomials of some degree, its roots define algebraic extension of rationals, and the higher the dimension, the more complex the system. This gives rise to evolutionary hierarchy. And the field body serves as a boss over a system to which it is associated, say biosystem. And it also induces a coherence of the ordinary biomatter. This is not a quantum coherence, but induced by quantum coherence in long scales. TGD predicts that classical gravitational fields of the Sun, Earth, planets, also other planets, they are responsible for very large values of effective Planck constant. I call this gravitational Planck constant. For ordinary particles associated with the gravitational monopole flux tubes. Same applies to macroscopic electric fields, for instance, Earth's electric field. Now I talk about electromagnetic Planck constant. Examples are electric fields of DNA, cell, ionospheres of Earth and Sun, and also large capacitor-like systems, in particular this Biefeld-Brown system. And electrons at monopole flux tubes for capacitor-like systems could be electrons, dark electrons, and this system would be this system X, about which I talked earlier. Pollack effect is the fourth new element in the model. The energies of quantum systems increase with effective Planck constant. And this means that the increase of effective Planck constant to kick them to the field body requires energy. In biology, this would be metabolic energy. And Pollack effect would provide this energy. In the Pollack effect, water is irradiated with electromagnetic radiation at visible and infrared frequencies. This induces a transfer of every fourth proton somewhere, flux tubes in the TGD framework, and a generation of exclusion zone. It has negative charge. It has stoichiometry H 1.50. It forms a layer-like structure generated by two-dimensional hexagonal lattices. And also it seems to have reversed arrow of thermodynamic time. It excludes impurities. And the proposal is that the protons go to the magnetic body or field body of the system and become dark protons with a very large value of effective Planck constant. More precise identification would be as gravitational magnetic body of Earth or Sun, so that planetary and solar physics would have important role in quantum biology. Pollack effect generalizes. The energy needed to increase effective Planck constant, it can come also from the formation of molecules as bound states of atoms. This could be essential for the formation of biomolecules and would mean a new kind of chemistry, allowing to understand the origin of the biomolecules, basic biomolecules. Also, electrons can be transferred to dark electrons at the magnetic or electric bodies. And in the case of capacitor-like systems, electrostatic energy could make possible the increase of effective Planck constant. Consider next the basic assumptions of the TGD model. The basic assumptions of the model reflect the observations already made. First of all, conduction electrons and valence electrons, they would be transferred to the flux tubes of electric field body as dark charges by the generalized Pollack effect. The effect is present in absence of external currents. This suggests that only electrostatic energy is used to induce the effect. This requires that the voltage decreases, and this in turn requires that there is charge transfer to the negative electrode, from the negative electrode to the positive electrode via field body. Only momentum transfer to the field body is possible by dissipation or by transfer to its internal non-thermal degrees of freedom. The large value of effective Planck constant suggests that dissipation is rather small. The electrons transferred to the field body from a given electrode can end up either to the opposite electrode or back to the original electrode. This makes possible generation of recoil momentum by pumping, in the case that some momentum is left to the field body. Pumping is must be more effective for a small electrode. This mechanism might be at work also when the dielectric is present. One can wonder whether the field body is associated with a capacitor-like system alone or with a larger system. One can think that the field body of Earth is also involved. For a capacitor-like field body, the motion is possible only in a rather limited region. This poses strong constraints on the applications. For electric body of Earth, larger scale motion could be possible, perhaps below the lower boundary of ionosphere. 100 kilometers is order of magnitude for a distance. The natural assumption is that the relevant part of the field body is located to the interior of the electrons. If the field body consists of monopole flux tubes, electric monopole flux tubes, then one has new mechanism of electron transfer, so that the casing would prevent this. It would be in dark degrees of freedom. Okay, the net momentum which is transferred should be parallel to a given monopole flux tube. This is rather natural from classical point of view. The recoil momentum is in opposite direction. The asymmetry favors momentum transfer directed towards the opposite electrode. And therefore the flux tubes should indeed reside in the intermediate region. Recoil momentum would be away from the opposite electrode, and the small electrode should give rise to a large recoil momentum. The effect would demonstrate the existence of monopole flux tubes as one aspect of this new physics. It is not quite obvious whether the effects need be large when the small electrode is positively charged. This is observed in Biefeld-Brown effect. However, if electrodes have opposite charges and the small electrode is positive, there is a net transfer of electrons to the positive electrode. Consider next a model for a capacitor-like system. The model for the capacitor-like system is inspired by the model for the electric body of Earth. TGD predicts a large-scale quantum coherence for charge systems with long-range electric fields. This could be highly relevant for the effect. The electric Planck constant for a pair formed by a charged particle with charge E electron and bi-charged system with charge Q capacitor plate is given proportional to the product of charges Q and E, and it is divided by velocity parameter, which is not larger than 1 when one uses light velocity as unit. One could assume that the values of velocity parameter are same for electrodes and the value is maximal 1. This assumption seems to work in many applications at the surface of Earth. This effective electromagnetic Planck constant would characterize charge particle at the electric field body, at the flux tubes. Electric field strength, rather than voltage, is relevant for the effect. The charge of the capacitor is electric flux, essentially, and in roughest approximation product of electric field strength and surface area of the capacitor plate. And the effect would become large for strong field strengths. And this suggests that the transfer of charges to the electric body is a collective quantum effect with a rate which is proportional to the square of the number of electrons transferred quantum coherently, rather than electron number itself, as in absence of quantum coherence. If the increase of voltage and in the experiments of Boole's team is achieved by keeping the size of system constant, as I believe, the dramatic increase of the thrust could be understood in this way. Macroscopic quantum coherence essentially. There is also a second parameter, electric Compton length. It is the same formula as ordinary Compton length, except that Planck constant is replaced by effective Planck constant, electromagnetic Planck constant, and it is proportional to product of charges, inversely proportional to velocity parameter and mass of electron in recent case. An interesting point is that for proton, this length is by a factor 1/2000 shorter than for electron, and this would explain why electrons, why not ions or protons. And this suggests also that in these original experiments it might be electrons and the same mechanism which would be responsible for Biefeld-Brown effect. Hitherto I have assumed that only valence electrons can become dark, and this is consistent with this. Can one assume that the entire electrodes form quantum coherent systems? Or should one assume that only the flux tubes are such systems? The entire electrodes need not be quantum coherent systems. This was found in the case of electric field of Earth. It is of course possible that a bundle of flux tube inside larger flux tube forms a quantum coherent system. So, if only a single flux tube is a quantum coherent system, a natural first guess would be that the flux tube radius D is roughly equal to the electric Compton length, so that one would have a formula in which this radius is proportional to the charge over capacity divided by the mass, and the charge would be proportional to electric field and surface area. By using values velocity parameter equal to 1 and electric field 300 kilovolts per meter, as in these Brown experiments, one obtains an estimate which is 24.3 centimeters if the scale of if the area is decimeter squared. This, at least to me, this makes sense. The orders of magnitude are sensical. If the small electrode corresponds to a single flux tube, it decomposes to smaller flux tubes near a larger electrode, giving rise to smaller quantum coherent units. And the ratio of charges Q large over Q small is ratio inverse of the corresponding ratio for surface areas. And this would mean that the quantum coherence, larger degree of quantum coherence at the smaller electrode. At larger electrode, there would be some number of these quantum coherent flux tubes, and each would, the sum of the contributions from these would give the total contribution. Here, one would have single flux tubes, and the contribution would be very roughly like square of this contribution from large flux tubes. So that it would explain the basic observation why the small electrodes are responsible for the effect. Why a smaller electrode gains a larger momentum, recoil momentum. The geometric asymmetry of electrodes, or more precisely, the convergence of flux tubes at the small electrodes, is believed to somehow explain the thrust towards the smaller electrode. One can imagine several options, but the following is perhaps the simplest one. Suppose that the flux tubes are U-shaped closed monopole flux tubes connecting the electrodes either via the region between the electrodes. Assume that electrons are transferred to dark electrons at these flux tubes, and the transfer of electrons to field body and back pumps the momentum to the field body and induces recoil effect at both electrodes. The simplest assumption is that flux tube smaller single flux tube acts as quantum coherent systems, so that for this single flux tube the effect would be proportional. The rate of pumping would be proportional to the square of the number of electrons. Suppose also that the smaller electrode corresponds to single coherent units, which splits to several ones near a larger electrode whose area is larger than the area of the quantum coherent region. Therefore, the charges associated with the flux tubes at smaller and larger electrode, they are inversely proportional to the areas of the electrodes. And this would predict that the quantum rate is much larger than a smaller electrode. I actually explained is more or less already. The rates would be in ratio which is square of ratio of areas. This would explain why asymmetry is important. Also, the net transfer of negative charge to the positively charged electrode when total charge of the capacitor system remains vanishing, such that the effect is larger for a positively charged smaller electrode. Of course, this model involves large uncertainties, but avoids obvious conflicts with what I have learned about this effect.
Okay, that looks like that's it. Tim, you're muted.
Oh, I'm sorry about that. I was just saying we'll take it down. Thanks, Mark. So Matti was not able to join us. Actually, I've been working with him off and on for 2 weeks, and he was able to log in, and now he's not able to. He's having bandwidth issues, and so it looks like he is not able to be here. We'll see. I don't have a new email from him, unfortunately. So I think here I'm going to stop sharing that. I think we've got a few minutes. We're a few minutes early. I mean, you know, we can. Did you guys have any thoughts on Biefeld-Brown? I mean, maybe we could take it that way.
You know who we should have here? Drew from sunny Florida. Where is he?
That's a good point. Where is Drew? Oh, and it looks like, okay. Okay. Yeah, and it looks like Ryan Wood is, he is almost here also. Okay. There we go. So yeah, so Ryan S. Wood, he is coming up next, and we could put him on a little early too. So, but yeah, we'll talk about Biefeld-Brown for a sec. Larry, you are doing Biefeld-Brown. You have a FlameJet generator thing coming up. Do you want to talk about Biefeld-Brown at all for us, or?
Yes, I can. I got the show on in the background there.
Oh,
there.
Okay.
Yeah, I had to do that. I was getting an echo.
Okay, yeah. So you've worked with Biefeld-Brown devices. I've seen at Tesla Tech, you've demonstrated
Yes.
rotators and things like that, right?
That is true. I built probably 6 or 7 of them in my time, and the one you saw was experimental. What I was trying to do was isolate so you wouldn't have the ion wind effect. That was the whole purpose of that. Tim saw this about 20 years ago. He was a kid then, and I still had some hair, as you can see. I'm entering my 72nd birthday on August the 7th. But the first one that I built, you can go on YouTube, and then under the very first one that I tested, we did a documentary on it, and it was called Search for 0 Point Energy. And it was presented prior to the Discovery Channel. It was the presenter had it on television. It was a 6-part series, And I was in about the first 15 minutes of it about T. Townsend Brown.
Okay.
Now, the unique thing about that particular device was in the background, you'll see it. It's like 8 inches. It's at 250,000 volts. It's got an 8-inch gap behind it, between it. In some of the smaller devices at 50,000 volts, they're much closer. When you raise up in voltage, in order to keep it from breaking down, if you're just using air, you have to extend out your from the positive to the negative several inches. That one was at about 8 inches, the one that I demonstrated in that video, and it was going about roughly 72 inches per second when it finally got up to speed.
It's a rotator. Yeah, it's going around and around.
And those weighed about 1/4 pound, the two of them. Later, I tested other units that were up to 1 pound, 3 feet in diameter, 18. You can do your calculations on torque and everything. These motors, I call them motors because that's basically what they were. If you were to put a gearbox in there, you could have generated a little bit of electricity off of it, in fact. But I built those, and when I built those, the first one, the one that Tim saw, I had reduced it down to about 2 inches, and I took a 50,000 volt, just a regular 50,000 volt wire, and then I sealed the ends of it because I wanted to keep any ionic wind discharge, just to prove the point that it can work. It can work through a medium, basically, other than air.
And so, Larry, what you were doing is really different, than what Drew was doing. So Drew was working at much lower voltages, right? With very low currents. You were working at really high voltages.
Right. There is I don't know if y'all know about the Vassimer engine, Dr. Chang De's. His is a variation of the Townsend Brown FlameJet Generator.
Okay.
And the way it works, it has a accelerator tube. It goes inside a chamber, and then he uses microwaves to excite the energy in there to produce a high temperature plasma. He made claims that he could, if we were to use such a system to get from here to Mars, he could get up to 150,000 miles per hour and be in Mars within 50 days. He has this engine that down in Houston, Texas right now. He is testing it as we speak. It's been running for more than 10 years. But he has been in touch with Elon Musk and NASA since he was an astronaut before. He's one of the people out there right now that's testing a unit similar to what Brown did with this FlameJet generator, except it's extended so that it can travel into space.
Well, and that actually, I'm really excited. So in a little while, we're going to come back, and I would love for you to describe the FlameJet generator, because that's a legendary part of T.T. Brown's work, and you are one of the only people I've ever met who's built one of those. So
yes, it was a learning process, and I'm building some more, and they're going to be bigger. I hope they work a lot. The first one worked okay, but anyway, excuse me here. In that one, the one that I built at the Tesla conference back in 2018, the whole purpose of that was to show, first to show that it could work. What he said worked, and it did. I used natural gas and also used CO2, compressed CO2 gas, to show that the moving of the gas through the capacitors would build a charge. I also built a downstream. I built it just like he said in the patent. He had a series of capacitors on the downstream side they were all different sizes, And one of the claims that Townsend Brown made in there was that you could, if you were to use this as an energy, a very efficient energy device, is you wouldn't need transformers. All you'd have to have is a capacitor and then plug into it. I had the first two capacitors were 20,000 volt capacitors. The next two were 400 volt. Then I had two 200 volt, one 100 volt, and one 50 volt. I think that's what it was, in line. And at the end of the 50 volt capacitor, when I'd plug it in, I was getting about 15 volts off of it. And if you plugged in at one of the bigger capacitors where you had your grid picking it up, you had a higher voltage. So what he said turned out to be true. That part, what he said was very true.
Okay. Yeah, it's remarkable. I love the fact that he's using chemical energy to boost that voltage. I love that idea. And so, and what you're talking about with the Vassimer engine, that's a really interesting comparison. Okay. Well, yeah. So, Drew, what do you? I mean, in terms of Biefeld-Brown, and you are no stranger to presenting on APEC. I mean, you guys are you guys are continuing to do work as well, right? Like, you have stuff in the last few days. Any changes there, or is it just kind of incremental advances?
Hello. I'm not entirely sure when Biefeld-Brown stuff starts or stops, but as far as my stuff, yeah, we've been incrementally processing, and we're moving forwards. And there's a test article in the chamber right now, which is basically printed frames. So I'm trying to build a stack of printed frames with propulsion plates in them. So, and big news! We got our first employee, sort of.
That's awesome.
New teammate, but he's going to be showing up 5 days a week to carry on the effort while the rest of us have day jobs, and somehow he doesn't have a day job and still survives, which makes us all very envious. So it's kind of cool.
Yeah. Well, so with what you guys are doing, the exciting thing there is you're proceduralizing things. And I went to Jim Woodward's lab out at California State Fullerton. They are doing the same thing. And it's almost like that is the next step in science, right? Is like all of us have started with like these novel, you build it yourself, like one-offs. And then as things progress, you as well as Jim, you guys are going to a proceduralized thing. Like you were talking about the frames, right? And when I came down there, what I saw was it's like build it and change one thing, build it and change one thing, right? And Jim was doing the same thing. And I was like, that is the next step. It was so exciting to see that evolution towards like this more professional test apparatus.
Yeah. And what I discovered is the guy that's coming in, he's a professional engineer, and he's kind of semi-retired, and if not 100% retired. But he's like, the first thing I'm going to do is I'm going to actually watch what it is you do and write it all down, because as far as I can tell, none of this is an instruction manual anywhere. I'm like, okay, that sounds great. When you get it all written down, let me read it so I can see if it's, if I actually understand what I do. So that's one of the big steps is to get the manufacturing process, which is still like you said, every single plate is a one-off. Just to stop tweaking the plates and start manufacturing them so that I can stack 30 of them up. That's a big step. We're just, we're kind of zeroing back because I've decided to build a free rotator, vacuum rotator. And, it's going to be difficult enough for people to believe that the thing spins. So if it looks kind of, not professional, it's going to be very difficult to believe that the thing is real. So we're going to try to make it look as professional as possible and as manufactured as possible. Hence the 3D printed hub and the 3D printed plates, and kind of a second person actually running the manufacturing process. I think that's a huge step toward We always talk about TRL, which is technical readiness level. It's on that NASA scale from 1 to 8. And I'm convinced we're at TRL level 5, maybe 5.5 or 6 even, depending on your viewpoint. But from an MRL, which is a manufacturing readiness level, which no one ever talks about, we're down around a 1 or a 2, or maybe even a 3. I mean, it's terrible. And you have to have that's on an 8 scale also. You've got to be all the way up to a 7 or an 8 with your manufacturing readiness level before you can actually proceed to become a real company and actually manufacture these things, and put 10 of them in your window and ask people to buy them. So that's what a lot of this next couple of months is going to be for us, is focusing on the manufacturing readiness level.
But that is so exciting. That's the evolution, right? That is the evolution of this technology. Is like you start out with an idea, you start getting results, you start to refine those results, and then you get into this path. And that is something that, like, as it gets better and better for everybody, other people will be following you down that road, right? Where it's like, okay, we have a pretty good idea of what we're doing. We just have to refine this over time. And then that's that manufacturing readiness level, right? It's like you create this test and refinement process.
Yeah, well, it's a very interesting, and I really had never thought about it because I lived my entire engineering career in the research and manufacturing and development. This is the first time I've ever stepped into the production side, or even thought about how is someone else who isn't me going to actually start from the raw materials on the table and assemble something, or create something that hopefully is exactly what I just did. And I don't know if I mentioned it, but I put out a video on our website, which is how to manufacture a little 100 micronewton thruster pack. It's foam and copper tape, and you got to go find your own 30,000 volt power supply, which I do not recommend. But it's a 35-minute expose on exactly. I mean, it shows you all the materials. It shows you what to cut, what to glue together, what to do what. So, that's my first foray into, manufacturability of a very 5-year ago design.
Yeah, absolutely. Well, let me see. We've got about 2 minutes left. So it looks like I just heard back from Ryan. He is trying to get into the studio. So we'll give him a couple more minutes here. And then if he's not able to, Larry, do you think that we could go right into the FlameJet generator? Would that be worth doing? I've got your video. I can put your video up.
Let's give him a few minutes, and yes, I can. Did you ever get my PowerPoint?
Yeah, I've got your PowerPoint. I can load it if you like. If I load it, I have to thumb through the slides for you, which I can do.
I've got it here already loaded up.
Okay, well, yeah. I mean, you can. Yeah,
you want me to control it because I'll.
Yeah, why don't you hit the if you hit the present button down at the bottom of your window, there's present, okay. And then there's slides. That. Oops, sorry, not slides.
I see that.
Yeah, slides. Yeah.
And then hit PowerPoint.
Hit your computer.
You see it?
No, not yet.
Okay.
Yeah, you have to add it to the.
You have to.
I may have to add it to my. You're right.
Yeah.
I was just gonna say there's 130 people watching, and we only have 2 thumbs up. So everyone, make sure to like and subscribe. That really helps the algorithm.
Okay, here we go.
Yeah.
May have to go back to. Let me see here.
Yeah, and again, worst comes to worst, I can load it for you, and I'll start us off. We got about a minute here, so we'll give Ryan another minute.
Okay.
And if not, it's not the end of the world. He might be able to, come and get an hour. We'll switch things around and try and keep it loose and relaxed.
Loose and relaxed. That's what we like.
Yep. Well, hey, this is like the dog days of summer, right? It's
hot.
People are tired. The whole 9 yards. So
see here. It's here.
Yeah, we got a tropical storm coming over Florida. It's probably about 12, 18 hours. So it's already started to rain here.
Yeah, we're just coming out of rain, which was kind of surprising actually. We had it was starting to feel like fall for a couple of days. And now warm back up. There's Ryan. Okay. Right on time. Right on time. Okay. Well, let me bring Ryan in. So Ryan,
Okay.
it is it is time to get started, sir. Do you want to try and upload your presentation? If you do that, you can thumb through it.
Yeah. Why don't you do it?
Okay.
We'll just do it that way. I'd love to, but I just finished up a 2-hour presentation in Menlo Park, and I'm running late, but
Yeah,
it's good.
No worries. Okay, it is uploading. Wait a minute. What's
Menlo
going on
Park,
there?
New Jersey, or California?
California.
Oh, Menlo Park is where Thomas
Yeah, there we
Edison
go.
started. Here in New Jersey.
Oh,
Okay,
Cool.
there we go. We'll add it in. Okay, so Ryan, thank you, sir. So you were talking about UFOs, anti-gravity, the whole 9 yards. We've got a slide deck. You got a bunch of about 50 slides here. So just let me know. I'm going to take myself out, but I will be here. So just let me know when to go to the next slide.
okay. Did you want to do an intro or?
I mean, that was my intro right there. So
Oh, okay. Yeah. All right. So let me begin by saying that I'm not an expert the way you guys are. You've been studying this field for a long time, and you know far more than I do. But I'm going to try to give you a perspective that's coming from uh, my personal experience and a ufological experience about trying to decipher the clues around gravity control based on um, the evidence that I've seen and so forth. And so that's what my focus is, or what I'm trying to share with you today. And so the next slide captures sort of what my father did. This is sort of the introduction to my world. Is that I'm 13 years old, and my dad tells me that hey, I'm working on anti-gravity at Douglas Aircraft Company, um, and he convinced his management to give him 600K back then, which is like 4.5 million today, to do interview abductees, to set up a Michelson-Morley interferometer and try to change the speed of light, to um, work on a whole host of um, physics experiments, the theoretical stuff as well as practical stuff, to try to figure out how gravity works. And this all started for him um, when he was at a meeting with his management, and they said, "Well, Bob, what are you doing for fun nowadays?" And he said, "Well, I've read 50 UFO books, and there's only one question left." And he said, "Well, what's that?" He said, "Are we going to figure out how this works before or after Lockheed does?" And that was the start of his funding for this, and his push into a deeper understanding of ufology. Um, and and I, you can see him. General Schriever is up with the missiles above, and my dad on the left in 1974, and then my dad 6 months ago, well, 9 months ago or so, at 96 in Newport Beach with me. Um, there are links that I can provide to the 157 pages of material related to Douglas Aircraft Company's gravity research and theoretical research. And it's interesting, but it's history, and I'm not sure that I have not fully mined it for insights, other than putting it in my AI ufologist AI GPT, gravity GPT as data. Why don't you go to the next slide there? Um, just again, it's fun. This is 1974 for me. I'm a senior in high school, and I set up a Michelson-Morley interferometer with a little magnetic field, trying to change the speed of light and try to look at fringe shifts on a pool table in Newport Beach. But I did enter the science fair and won first prize at the Orange County Science Fair. But that's sort of my early indoctrination. I was 19 years old there. At that time, 18, 19, I think. And that was my genesis. And then I sort of ignored it other than ufology until last year and started to get more serious. Go to the next slide about ufology, or not ufology, but anti-gravity. So one of the first interesting things is this guy, Dudley Bowen Clark. So out in the desert in 1951, he had, $6 million down a dirt road with contracts with the Atomic Energy Commission and Navy and Signal Corps, working on an gravity insulator. So that was what his team was working on. And I have a large file on him, and I've requested his FBI file. But I find it very interesting that, here's the first thing that resonated with me. I mean, gravity control may have gone back to the Nazis and earlier, but for me at this time, I'm thinking that this is sort of the origin point of progress. Next slide. Did you get the next slide there, Tim? There we go. And here's the newspaper article that sort of talks about this in detail in 1951. Next slide. And then you may have seen this before, this New York Herald article where the guys at Convair and General Dynamics division were doing work in 55 on spinning magnets and spinning permanent magnets. Maybe high speed, those look like air bearings maybe, or they're working on that sort of thing. And this is your sort of first clue that spinning magnetic fields is key to an understanding of how to break through gravity potentially. Next slide. And then you may have all seen this picture of the G engines are coming in 56 in Young Men magazine, and mentions of Glenn Martin, which we'll talk about more, and the other key people, including Clark Electronics Labs at the end. But I'll mention that this guy, Michael Gladwich, that wrote the article, was a World War II fighter ace in Poland, then France, then in the UK, and was injured, but very much plugged into the entire aerospace world in a detailed way in these 50s timeframe, and participated in a lot of behind the scenes meetings. And to my surprise, he wrote a book on Admiral Byrd on Antarctica, for those that are following the mysteries of aliens in Antarctica. But I find that interesting, as sort of a plausible connection. Next slide. And here we get to the mother lode, in my opinion. This is the Glenn L. Martin starts this Rias group. Walcom Bender was the leader at the time. But he starts it in 55, and all these super powerful, heavyweight theoretical physicists and mathematicians are working hard at trying to figure out gravity and gravity research. Lewis Witten has got videos about bismuth magnesium, and people recognize Rudolf Kalman for the electronic Kalman filters, but ... I've requested FBI files on a lot of these people, and we'll talk more about George Trimble in a little bit, a few slides later. and his involvement with Lockheed Martin's. So in the next slide, we'll also talk about, in the 1960s, NEPA was canceled, nuclear propulsion of aircraft. Why did they do it? Maybe they figured out gravity, or they decided, well, there's lots of potential reasons why you wouldn't want to have a flying nuke around. But the newspaper articles on gravity stop, and there's the counterintelligence effort probably to squash them or not support them. NMR, nuclear magnetic resonance, is transitioned from sort of a pure research mode, which Asloff and others will highlight, to more technology focused, where let's just make an MRI machine to do something. And then, as Hal Puthoff and others, and Tim no doubt understands, that string theory kicks off in '68 as a potential cover story for how to push the mainstream physicists down a track that's a dead end or a mildly useful end. So anyway, I'm just sort of commenting on that. And the next slide. And then you may have all heard about Ben Rich's efforts at the Lockheed Skunk Works for 15 years. But I'll pull you to the third bullet. Is that there's an error in the equations, and we figured it out, and we know how to travel to stars, and it won't take a lifetime. When I think error in the equations, I think these are human beings figuring out errors. And GR is not correct, and they fix that, or Maxwell's equations are not correct, or the combination of the two, or scalar functions are not correct somehow. And so they figured it out. And I don't think the ETs are giving them equations on a they wouldn't quote figure it out. They would just be given the equation. So anyway, I find that highly suggestive that it was us that figured out how gravity works, rather than some sort of celestial gift from others. Next slide. I'll give my shameless plug for the second edition of Magic Eyes Only, which is on Amazon. It's got 104 UFO crash cases from around the world, and it's updated from my first edition, which had 74. But for those people that are interested in UFO crashes and some clues in physics, but not nearly as many as, say, Paul Hill's book, this is an interesting read. Next slide. So now I'll sort of talk about potential man-made anti-gravity crashes, or cases, excuse me. And I'll have to credit Michael Schratt for his work on finding some of these and illustrating some of these, and highlighting the fact of their man-made nature. We'll talk a little bit about the Danielson, Connecticut case, and then the Eddie Laxton case as well. So the next slide. So November 20th, 56, this woman stands outside. She's got this 25-foot cross craft with these very detailed drawings. These are drawings of these Tesla coil type tools, or propulsion systems. No sound, heat, smell, hovered, maneuvered. It looks like insulators on transformers or Tesla coils and so forth. I just find it interesting that in my mind, this is another potential clue as to the nature of how gravity works, as well. Next slide. Tim, you there? Next slide. Counter rotation. So that's another principle that I find interesting, is that there's several cases where you can clearly see both sides of the disk rotating in opposite directions in a counter rotation manner. And so that's the another interesting aspect or clue to the nature of gravity control, as well as this hum, this noise. And this was investigated at the very highest levels, military officers in New Zealand where it happened, as well as the U.S. and so forth. So again, that's I think a fascinating other clue to the nature of how to do gravity control. Next slide. And now we come to the one where I'm sort of staking my my position on is this Eddie Laxton case in Temple, Oklahoma. So this is a Air Force electronics, like 15-year veteran, driving to work, rounds the bend, sees this craft parked in front of him with this huge electrostatic wick behind the back of it, and a man standing out in front. And he gets out of his car and walks towards the man, and the man notices him. He gets in, and they fire it up, and this low-level hum starts, and he takes off, flying away very rapidly. And there was another witness to this effect too. And the next slide shows his drawing, his first-hand drawing, showing a horizontal stabilizer on the rear, and then these lights, and this little standard fold-down gangplank, and a human being. And this is this is his first-hand drawing with the letters TL4768 on the test lenticular device or something like that. Next slide. So it's interesting, this is his comment. What I saw was definitely not from space. The man was wearing fatigues, had a hat, bill broken up, Air Force mechanics, common English letters on it. So the next slide, he was clearly impressed that this was a human being. This is the Blue Book card that had multiple witnesses, and a mention of this hum, this buzz that occurred as this craft lifted off, this and that humming whiz noise or increasing pitch has occurred in several cases. Next slide. So when I think about the problem, I think of, if this is working in 66, they had to have designed it in 64 or built it in 64. Maybe they figured out anti-gravity in 62 or earlier, or maybe this is one of earlier ones. So this is highly supportive of that. And you got to realize on the left, these are the technologies you got to work with. You've got to work with analog dials, you got low altitude operations, you got high power vacuum tubes, no advanced semiconductors, you got magnetics, you got electrostatics, you got magnetism, you got barium titanate, which is a capacitor, dielectric. But you don't have some of the fancier stuff. You don't have any fiber optics or carbon fiber or GPS or squat. So you got to think in the mindset of, we should be able to do gravity control using 1960 technology, and it should be possible to do it that way. Next slide. And now I'll take you to the orange juicer with tentacles in 67. So Bill is watching television in his house, hears the dogs barking, and goes outside, static electricity everywhere. His arms are all up and head, and he sees this craft with these electrostatic wick tentacles and these little gooseneck spotlights coming out of the craft. And in the distance, he sees other craft hooked onto the high tension power line, glowing red, pulling power out. He sort of freaks out and gets his wife and kids, hops in the truck, drives to the neighbor's house, and then, the neighbors and everybody watch it for a while, and then it all disappears. So again, electrostatic seems to be another key clue as to the nature of how to do gravity control, high electrostatic fields. Next slide. Another example in Venezuela, where it looks like those are flame jets, but there's sort of plasma glows on of this man who's in his apartment looking out, 100 feet towards this craft, and this this sort of, two hemispheres with electrostatic fields or lightning going back and forth between them. And so that's very interesting. And then the craft leaves, and another one shows up or nearby, identical in the same vein. So again, another example of potential man-made craft. Next slide. Or this one I'm less sure about, but it's the flying pyramid, and it's the motorcyclist. His motorcycle gets totally demagnetized, doesn't work anymore. He gets radiation sickness. But I just find it interesting in that, one of the ways to make an asymmetric capacitor is to do it with a pyramidal shape. You could do it with other shapes or geometries as well. But I find that interesting and suggestive, maybe not as strongly as many of the other cases. Next slide. And then up in Canada in 2013, we had this barbell UFO case where it's slowly rotating around the center axis, and emitting sort of electrical spark-like shower or plasma glow around it. And then, 6 minutes later, a second craft, identical one, shows up. Two identical craft just seems suspicious in my mind. But anyway, this is another potential interesting case that could be man-made. Next slide. And then you get to the hunt for 0 point. Many of your readers, and I think, Tim, you've interviewed Nick maybe before, a long time ago. And, the arch villain is this guy, George Trimble, who worked at Lockheed Martin and refused to talk about his firsthand experience inside Lockheed Martin around presumably gravity control. But the sort of summary of the book, in my mind, was that anti-gravity is bound up in counter-rotation, torsional magnetic fields, or torsion and magnetic fields, 0 point energy naturally, which is where the energy I think is coming from, nuclear spin, and electrostatics. There may be some more subtleties, but it's not just Nick Cook who couldn't get Trimble to talk. It was Tom Vallone as well, and maybe others. But from my perspective, I want to interview Nick Cook or Trimble's kids and grandkids and find out what they have to say. And I've filed for Trimble's FBI file as well, which will be interesting reading if it's blacked out, or doesn't exist, or what have you. So that's where I'm going with it. Next slide. And then many people may or may not know of Paul Hill's Unconventional Flying Objects book, Scientific Analysis. He's a NASA engineer, collected all these case data around UFOs. And, these are the key attributes. No real surprises about the magnetic fields or electrostatic fields or, shapes or high G turns like or the Tic Tac videos or other videos that you saw in Skinwalker Ranch, or the high speed G turns with squishing people. We all know that's something that's not. It takes gravity manipulation or inertia control. Next slide. So something else people probably don't know about is the Encyclopedia of Flying Saucers. This is original onion skin leaked document after 39 years. It says highest classification of the document, top secret magic. And what's interesting about this, besides some handwritten notes by Vannevar Bush and others, is the next slide, which has this comment, but to all these things, rule out the possibility that saucers are man-made. And the handwritten note is that this should not get out, is the key wording in ink by some military or scientist in the mid 60s saying, in a classified document, this should not get out. So implies in my mind another secondary source that we have anti-gravity technology in that time frame. And we've done forensic testing of the ink and paper and pen marks and the top secret magic stamps and all that stuff. We can talk later about that. But next slide. And then, David Froning is mentioned in several articles about AFRL. What they want is proposals that focus on high voltage, high frequency electromagnetic field pulsations to induce mass fluctuations within electronic and ionic structure and dielectric materials. So that's where, the sort of government military sort of wider world. I don't think this is the top secret people that know what's really going on, but that's where they think the answer lies. And I find that interesting. And I think I agree with them. I think that the answer lies to gravity control in those paragraph and other things too. Next slide. So, this is the conundrum. Now what? And this is what I ask, so the only thing to do is to rediscover it and prove it in a credible, public, open way. Next slide. So that's what I'm focused on. I find this article interesting. Graham and Lawrence in 1980, they're sparring back and forth in Nature about, the predictions of different Minkowski tensors and Abraham tensors in all a credible way. I think there's something to their debate back and forth as to being clues to the nature of what's really going on. Next slide. And then, you guys may have looked at the triode vacuum amplifier and the mysterious death around his involvement and various other people. What I took away from it, other than, here's another potential over unity device that's kind of intriguing, was the whole bifilar winding approach in potentially a device. But I think it's likely a dead end. People have tried it before and not made any progress. But I'd be curious to hear what your opinion is, Tim. And next slide. And then, Madman Markham, many of your audience may or may not have heard of Art Bell's. You can listen to this whole thing with his Jacob ladder and potential time machine and gravity manipulation. But what I took away from it is he's using high voltages, 20 kilovolt, 3 megavolt, and electromagnets and vortexes. And so again, these are just sort of clues in my mind to something weird happened with this guy. And despite him going to jail and other baggage associated with his experience, but he got out. I mean, it was just for stealing transformers, but harmless crime in my mind. But anyway, the next slide. Is Boyd Bushman. He was interviewed in Nick Cook's book, but he has this north pole magnet test where you put two north poles and a north south pole and drop them off 4 stories, and the north falls at a different rate, and it's been repeated several times. And this is interesting in my mind in that it's a fundamental physics thing that's changed. There's a clue again about the nature of how to control gravity. I got his FBI is in hand, lots of anti-gravity mentions, but he also has a long interview about Area 51 and his comments that Richard Dolan did and others, which I sort of push off to the side and ignore. But nevertheless, I think the concept of this north pole falling at different rates is another interesting clue. Next slide. And then, you've interviewed Poklanoff and Ningley, and Ningley's dead, but the point is that there's a lot of interesting stuff in this Ning Lee's FBI file is on its way to me. We'll find out the truth whether or not she was really escorted out of the country or left or not, and a lot more details about what really went on with her. I did note that George Hathaway, did not see any effect repeating this experiment. And Tor, or Ning Lee's partner, also, continues in doing a bunch of classified work around gravity, presumably. At least that was what's going on. So I find these people interesting. You wonder why Podkleinoff is not all in on doing more direct experiments on gravity, but maybe he is, or maybe he's some other motivation. Next slide. And then Frederick Alsvan, which you've interviewed before on your podcast, which I've watched with great interest, Tim, and good job there. But I think that his original science there and equations and perspective is actually pretty interesting in this dynamic nuclear polarization. Could lead to gravity control. Again, that's another key clue in my mind. Hathaway and Dan Alsifan have collaborated on working on this with, as Hathaway said, ambiguous results. So I don't know if it's going to work or not, but people keep doing experiments, and by Jove, that's good. Next slide. Tim, you got the next slide? Well, I won't highlight the book, but the book's there for getting what's going on, and fluctuations of intense black body radiation influence the propagation of light signals, leading to measurable deviations in space-time intervals. So that's their core hypothesis. The question is how to test that in a robust way. Next slide. Hathaway's perspective on John Hutchinson. I've read Hutchinson's accounts and familiar with a lot of the spoon bending work of Jack Houck and so forth. And clearly the guy has, some innate mental psychokinetic ability, sort of a technical psychokinesis. Later in life, I think he faked some stuff, which lowered his credibility. But did he really fundamentally have some mechanism that he could use his mind or some other technology to manipulate materials and metals? Maybe not with a gravity effect, but maybe with, I'm not sure. But I find it interesting. It's, again, it's another anomalous data point that may be totally linked to gravity control. Next slide. And then you have the bismuth magnesium part, the Roswell part, which people, Linda Moulton Howe sold a couple pieces for like $30,000, and people are working on trying to figure out this bismuth magnesium, zinc, and aluminum or iridium. Apparently, the iridium atoms are spaced every atom over, which I don't know how the hell they measured that, but there's a line of iridium atoms. And the rumor is that frequency, it levitates. But Hathaway investigated and didn't find any shielding, and but he didn't use terahertz frequencies, and there may be something to it. But I find it interesting that there's some opportunity there to keep investigating, and science will push along. But it's still problematic. Well, how do you make the damn stuff? And that's not, you can't just put it in your 3D printer and do it. So anyway, the jury's out. We'll know in a few more years, I think. Next slide. This is fresh and new. This was at the Dallas MUFON July 13th, 2024 Metamaterial Conference, or actually it was it was the MUFON conference. They had this big reveal. They put out a big press conference about it. And apparently, the witness said it came from Russia a couple times. It's super lightweight. And they used this handheld XRF, and it was calcium, iron, copper, titanium, but no graphene at all. And it was super light. They had it pictured on top of a flower. This particular picture is not the right one because I didn't have my camera going fast enough. But it was interesting to see that that material. So that was fun. And I find that interesting, but it's basically just a dielectric. I mean, you think about calcium copper titanate, which has a K factor of like 100,000, and maybe this new metamaterial has uh, an equal K factor, but it's light as a feather, so it's really it's dramatically different than um, other potential dielectrics, which might be associated with asymmetric capacitors and propulsion systems. Um, next slide. So I did create this, custom private anti-gravity GPT. So I've taken, along with my other fellow cohort in crime, Chris Ekman, we've taken a vast number of gravity related books and journals and periodical and trained them all with a custom um, AI tool and sort of had it work on a dedicated data set and start to ask questions of it to better understand insights. And we're trying to work on remote access so that maybe ultimately your team can explore what the tool has to say about a particular aspect of anti-gravity control and things like that that might be useful. In my real business as the CEO of Electric Fusion Systems, we've used a similar tool that's all trained up in fusion literature, and it's been highly helpful in just exploring quick ideas and getting calculations in many cases back that is highly useful. So um, next slide. This is another interesting article by a couple of Italians, quantum vacuum energy, gravity manipulation, and force generated. So I don't claim to understand it all, but I find it interesting that these people are working on it. And in that article, they highlight the next slide, which is this sort of asymmetric ZPF shape where you have a high frequency region and a lower frequency ZPF region, and it pushes the force forward. So is this a clue as to how flying triangles that are in the UFO field work, or the pyramid shapes or the ice cream cone shapes work as well? So anyway, I just find it suggestive that there's some clues there that are worthy of experimentation. Next slide. And then you've interviewed Brandenburg, I think, before. He got this 200K DARPA contract to write up his theory on gravity control and claims to have a 7% mass reduction in his experiments. But my comment to that is, well, if you got 7%, well, where's the scale up? Where's the next level? Why haven't you made one that's a hell of a lot bigger, better, fancier, etc.? So I worry that there's something not really there. He talks about this vortex of pointing vectors as key takeaways, and I think there's something there as well. But fundamentally, it lacks mainstream validation. It hasn't been repeated. the standard model of particle physics and general relativity don't support this, what he's doing. And, but this is the usual diatribe they say to all of us who are working in the gravity field. Next slide. And then, so, I go to this, this is my set of thoughts about where the secret lies. And it lies in a lot of these different aspects. And you can read down, and we've talked about many of them before. So now the question is, in the next slide is, now what? How do we take it to the next level and move forward in the next slide? So I'm focused on interaction with magnetic fields, electromagnetics, electrostatic, high voltage capacitors, and I want to use Michelson-Morley interferometers to measure the changes in speed of light, which are relatively straightforward. And next slide, to put your test apparatus in that and see if you can get fringe shifts that are dramatic or show. I mean, it'd be great to measure, mass changes and the damn thing got lighter or floated off the bench or on and on. But I think that realistically, you may want to start with this, or if it doesn't float off the bench, put this in place. Anyway, but you're familiar with that. Your audience is familiar with that, I think. Next slide. So here's sort of my first iteration of an approach, and I keep evolving it. Again, I'm sort of new to this, but I'm doing my best. So I started with spinning permanent magnets with motors and Helmholtz coils with bifilar windings, and then I threw in some asymmetric capacitors in the middle. It may be wrong to have two. I may only have one. Might want to put it at 90 degrees, and you can do. I added an electrostatic flap in between the Helmholtz coil and the spinning magnets to create sort of static electricity. So it's a combination of a Van de Graaff generator, Helmholtz coils, and torsional fields from the spinning magnets, and you can vary the winding voltages and currents and measure it. The test matrix on this is nasty as hell, and there's a lot of different tests that can be done to see if you get any responses. And the next slide. So here's sort of a picture of my workbench and work in progress, as doing a variety of the tests using RC motors that spin up to 15,000 RPM, and I made some custom plastic holders. And when you start building things, it gets a lot more real. Next slide. And here's a picture of an asymmetric capacitor that I'm working on. I may make it actually the Giza pyramid, geometry, but in essence, you got to get the CCTO from China because the U.S. doesn't sell it really unless it's outrageously expensive, and just so everybody, the K factor is up to 100,000, and you can mix in bismuth or magnesium, or bismuth most realistically, because it will sort of melt at a lower temperature or when you press this whole thing together and sinter it, because you have to. The calcium copper titanate is you sort of have to squeeze the shit out of it for like a day, 30,000-40,000 pounds, 15-20 tons, and then you put it in an oven for 10 hours at 800 C to sort of really sinter it all together, and then you hit it with a water jet and cut the shape that you want, and then you can start doing experiments with it, of square waves and pulses and see what you can learn about this weirdness of asymmetric capacitors. Next slide. Here's another proof of concept one where I put a ring of capacitors up to 50,000 volts in series in the middle with some bifilar windings or not. I don't really know about that. And then the spinning permanent magnets trying to look at a different set of test things. This might be generating electricity as well, or some sort of gravity effect. Or some physicist is going to call me afterwards and say, "You got this all wrong, Ryan. You ought to do this, this, and this." And so I'm open to that. But anyway, let's go to the next slide. And then, so sort of the final thing is, let's investigate and rediscover, which is what Tim's been doing all along, is championing the whole reinvestigation effort and trying to get people to communicate and figure this all out. But I guess what I bring to the table that other people may not is the investigative journalism in me, where I'm going to get a lot of these FBI files and I'm going to find and interview a lot of these people that know something. I'm going to do some remote viewing targets. Because I've used those people before to try to understand what happened in the past and what could happen in the future. And then ultimately, you can find the R&D teams in corporations. They're people, and you can start to do that. And ultimately, in the end, which is our goal here, is to build it and test it and prove it in a public big way, because this is the giant crime against all of humanity, is that we could have had the free energy and allow for an upgrade of water and food and energy and aviation and environmental control, or not control, but improvement, and move the planet from, where 1/3 of the people are starving to death and don't have a high school education, to something far better. And so uh, with that, I think that's the last slide, unless there's another slide after that. Oh yeah, why invest? Well, I'm walking for ideas or investment, so, but you sort of knew that. And I keep doing it on my own because that's what has to get done. So with that, I'll turn it back over you to Tim and the chat and Q&A, which will probably blow up.
Yeah, well, I'll tell you, Ryan, let me bring everybody back in, and let me apologize. I'll bring Bernie in there too, and I will take that down. So I was guzzling coffee all morning. So these were like me trying to sneak out the back, because I was like, running in. I'm like, use the restroom. Okay, come back. So, but yeah, again, thank you. That was an amazing presentation. So everybody, let's give Ryan Wood a big thank you. Ryan, thank you so much. That was, again, amazing. You covered so many different topics that we've talked about on APEC, and you had sent your schematic to me actually a while back, and I was like, that's really cool. It looks a lot like the Graviflyer in some ways, but you're hitting a lot of unique, like, technical aspects. So
yeah. Well, there's let me push on the chat button. Okay. Well, are there any questions that we could throw out to the floor?
I've got a question. Did you use the Dan mode of ChatGPT in your work with it? The no restrictions.
It was well, there's multiple comments there. What I did is I took all the data that I had and scanned the PDFs, OCR'd the PDFs, turned them into JSON format, put them into a private dedicated AI database that Chris Ekman had written for me, or for him. And we had multiple AI agents answering the queries, and the query gets served up through ChatGPT for Omni API. So I don't know what Dan mode is, but hopefully that clarifies what we did.
Dan is the do anything now direction, so it like jailbreaks it not to have restrictions. But
Okay.
yeah,
Well,
maybe
it's about
try
the-
that, and it might give you extra unfiltered, unregulated answers and give you a real breakthrough.
Well, I mean, it's about the data in my mind. It's like the data that I put into it, GPT doesn't have, you know.
Yeah,
Yeah.
we did something similar.
Gotcha.
How
We
do
did
you
something.
keep from getting into a false logic loop? I mean, you it's like laying 1,000 books on a table and assigning all of them as true. Well, the computer doesn't know which one of those 1,000 books is full of nonsense or fiction or a guy's best guess. It just assumes all of them are true or none of them are true. How do you
That's a good-
account for any of that in this new
Yeah.
wild and
Yeah.
woolly world of AI?
Yeah, well, that's a great question, Drew. The answer is it's
The
still
hope-
a garbage in.
The hope
garbage
is
out
that the
problem.
truth is aligned.
Yeah, it's still a
What?
garbage in, garbage out problem. And,
Falseness is usually in random directions.
Yeah, okay, that's a good.
So if
input.
most people say the truth
Oh, sorry.
Yeah.
I
the
think
truth can rise to the top of. Sorry.
Yeah, that's a good
No,
point.
it doesn't
Just-
work that way in engineering. You can have lots of ideas on how stuff is put together and how stuff works and how materials should work, and it's like a wing. You can load in all of the lift curves you want, but you don't know which ones aren't real.
Well, I think it's
So,
probably weighting.
Yeah, there's some truth
That
to
would
that.
be my guess. I think
Yeah.
that they probably use weighting, and then
Yes.
I would guess they use like repeat data elements, right? And so
Yes.
I mean that's how I would do it. I've seen stuff like that where like a search engine does similar things in some ways. Where like if you see the same statement multiple times, they'll give it more weight, and so it's more likely to be true.
Yeah.
As for the Alzaphon parts that you brought up, I actually have all of the equipment that Daniel and Hathaway worked on. This is the S-band setup. So one of the reasons why they didn't get very good results is because Hathaway had this idea to work with a ruby crystal instead of aluminum. And his logic was, well, it has an aluminum atom in there along with chromium. The problem is in order for electron paramagnetic resonance to work, you need to have those electrons free. If they're busy doing other work, then it basically is a dielectric, and the electrons are no longer free. So the entire purpose of using aluminum was wasted by going with an oxide or a compound of aluminum. They did, however, see very strange effects with the X-band system, when they actually ran the experiment at cryogenic temperatures. They saw the sample was moving around a lot. We have run experiments with liquid metals, with actual metals, not liquid, aluminum powders inside of epoxy, and we saw weight loss on the order of like a 0.75% weight change. David Chester actually helped me write up the paper, and we presented it at the Experimental Nuclear Magnetic Resonance Conference. And it was very repeatable. There was a couple different variations of it, like the effect sometimes flipped. And those are still things we're trying to understand why that happened. But right now I got the S-band system from Hathaway. We're going to try it at a lower frequency, which hopefully we'll have better penetration into the sample and get better signal to noise ratio.
Well, that's great, Mark. Thank you for that clarification, and good luck. I mean, I think Hathaway's good, but at times he's narrow-minded.
And so I would say he's an amazing experimentalist, and he's very meticulous, and sometimes you can be too meticulous. And the cases where you're too meticulous is where you try to control every variable and get the most sensitive equipment possible to the point where you never run the experiment. That's when you're too meticulous. And there's many projects like that at his lab where he's just like, oh well, I wanted to do a little overkill, and then the project's never done.
That's where you set up you spend more time setting up the experiment to do it, and then you spend 1 minute doing the experiment.
It's usually like that. Most experiments are usually like that anyway.
It's always like that. Yeah.
But if you don't have
I was gonna say that sounds like every experiment for sure.
I've seen that with a few. One of the things that I suggested was for experiments like that, like maybe having like a beta version and then a stable release, kind of like they do in software. And that way, because you want to have that rigor, right? Where you're like, okay, change one thing and test. But the problem is, like when you look at Elon Musk, okay, they kind of go hog wild and change a bunch of things at once. So if you have a couple of versions, you can do like change one thing over here, and then it's like, you know what? We'll try one off. We'll try 10 different things, and maybe 3 of them will work. So
yeah,
that's how I double up on my experiments. I have double coils, so I'll set up one experiment, then set up an opposite experiment, and just one after the other. Run them in series.
Well, because like Larry was suggesting like a moment ago, I mean, sometimes your experiment takes a long time to set up, right? And so it's like, okay, change one thing and test sounds great, but then if it's like 4 hours to test, it's like, okay, that sucks. You'll find out, you'll get to where you want to be like 5 years from now. So it helps to have like, a little bit more flexibility sometimes, I think.
Yep. Well,
Awesome.
I have a hard stop here in 4 minutes, but any other questions?
You know what? Oh,
sorry. Your dad was worked with McDonnell Douglas, right, Ryan?
He worked at Douglas Aircraft and then McDonnell Douglas. Yeah.
Yeah.
And then,
my stepfather worked at LTV in Fort Worth, and for the longest period of time, when we'd go to parties, we'd be talking about UFOs, and he'd go do 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 do, making fun of them. Well, after he read Subquantum Kinetics, Paul Olivet's book, and then the second one, The Secrets of Antigravity, he knew I was involved in doing this kind of research. And he told me, he says, I used to see flying saucer drawings and top secret drawings come across my desk all the time. He was a physicist, and the last thing that he designed was the A-10 Warthog, which turned out to be one of the best military planes that there was. Yeah. But he said all the way back to the 50s, and he said up until about 1975, and then it just cut off suddenly.
Yeah, interesting. Well, that's good. I mean, the A-10 Warthog is what they need in Ukraine right now. Mm-hmm. But thank you for that story. That's great.
Yeah.
Yeah. Awesome. Well, I think we're just about there. I mean, if anybody has any final questions, that's cool. Otherwise, we should give Ryan Wood another giant applause. Gentlemen, thank you so much.
Absolute,
Ryan, thank you.
Excellent presentation. Thank you
for running through so much stuff. Sorry about being slow on the slides. I fully admit to having the world's smallest bladder. So.
Okay. All right. Thanks so much, guys.
See you.
Thanks again.
Thank you.
Thank you.
Okay, so what I'm going to do is take everybody out now, except I think we're time for Larry. I think this is your presentation, right?
Yes.
We're rolling on that.
I'll let you run the slides. It'd be better because
okay. So what I'm going to do is in the background, I've got your video queued up, so I will take myself out, and but let me. Okay, I'm going to share screen. There we go. So you've got, and what I did was I redid this presentation so it play at maximum size, and I'm going to take myself out, and actually I'll just take both of us out and play this thing full res for just a moment.
Okay.
Now, what you see here is the FlameJet generator. Originally, I put a blower in it to run air through as an intake, the same as a jet engine would be, and come through here. Because this is not closed today, we're not going to use the blower because it's open. I'm going to have to run it without the fan jet, but I will use compressed air to simulate the same effect that you would have if you had air coming through it. But it'll come through here, this high voltage system will be turned on. It will charge the gas up here, pass through here, and charge each one of these plates up. Now, between each one of these plates, there's a 20,000 volt capacitor, and the wire connects here, and then it goes through the capacitor, and then it goes to the plate. And they're series, they build up. There's 11 of them. On this side, you'll see the same thing. You'll see the wire come in, and the same way be grounded and come through here to each one of these plates. What Townsend Brown said was that this should charge up enough voltage as it passes through it to build you a high voltage on the exit end. You will see the exit end right here. You'll notice that it's open and hollow all the way through until all the way to where the gas comes in from the jet flame burner, and it comes through each one of these and comes out on this end. I will now turn on the high voltage source and give you a demonstration. You'll notice that there is a spark coming off of it, off the ball. And when I turn on the jet turbine, it'll actually start discharging a little bit, hopefully on this ball next to it, which is hooked to the high voltage source on the end. I will turn the gas on and I will light it and show it to you right now. You'll notice it. Down here's the gas valves that go to it. Purge that gas out a little bit. I will light it off and then I will show it to you. You can see the flame coming out. You can actually hear the flame carrying the charge across to the other side. We'll turn the air on here a little bit. See that the flame is lit. Now you see it charging up on this end. About a 3/4 inch high voltage rocket system. See it there again. So it is working. It is discharging. It is building a high voltage field across this discharge side. That will conclude the demonstration of the generator this time. Thank you, everyone.
Awesome. Larry, that was amazing. That was amazing. So, and you have a presentation for this too, I think.
Yes, I do. And that was the very beginning.
Do you want to try and upload that? Were you having problems with it?
I was. You can go ahead and show it if you want to.
Okay.
It's been a while since I've been on Google and done the presentations.
No,
So
that
I'll
is
let you go
okay,
ahead and
sir.
upload the presentation if it's okay with you.
Yep. Okay. It is processing. Yeah. So
Okay.
it'll take just a second.
I wanted to
load it
say
for you.
that was the very beginning. I redid that generator later when I moved to Michigan. I lived up in Michigan for 3 years. We had to move up there because my stepson had some health issues. And so I moved up there and finished, redid it. And I changed a few things around on it.
So Larry, just for the audience, and
Yes.
I could be mistaken on this, but from what I remember, basically you're using chemical and mechanical charge separation, right? And so you inject a low voltage at high current into the flame, and the flame itself, because it's moving out, it creates that charge separation that raises the potential, right?
It was actually it was a high voltage. It was about roughly close to 50,000 volts.
Okay.
And around 7 milliamps. And you inject this into the flame, and as it goes across each plate, of course, it builds up a voltage in the capacitors and it charges it up. On the initial output, it was around 250,000 volts. When we did it at the Tesla Tech convention in 2018, I had to use CO2 gas inside. I could not use the flame inside. We tried it outside. We ran it outside. I had some issues with it, so I switched. I knew I could run it with CO2, which actually worked better, believe it or not. We turned it on and we'd run the gas through there it took about 5 to 7 minutes to discharge 2,500 pounds of CO2 through there. And on the initial startup of the charge, it would be about 242,000 volts. It got up to about 260,000 volts, and then it would diminish as the pressure began to get lower and lower. But it did work, and we were able to get readings off of it. I will go into we'll start here with Townsend Brown. Of course, most of you out there know who Townsend Brown was. He was born in Zanesville, Ohio, to Lewis and Mary Brown. And his dad was a wealthy contractor and developer, built houses in that area. And Townsend Brown was born in 1905, I believe. And at a young age, he was very interested in science. He acquired a Coolidge tube, which was an old X-ray tube, and had this idea that you could use the high voltage on it to move things. So he hooked up this Coolidge tube to a contraption. I don't know exactly what it looked like. It might have just been a pendulum, like a pendulum effect. but he would turn it on and he'd notice it'd be moving. He was smart enough that he began to realize that this Coolidge tube was producing this effect. And as he got to investigating, he realized it came from the capacitor. It didn't come from the Coolidge tube itself, these rays from the Coolidge tube. This was around about the time, I'm going to say he was probably 12 to 14 years old. There was an article, according to Paul Lavalette's book, Secrets of Antigravity. He shows it in there if you read it. It's a small copy of the Ohio Daily, I think is the name of the magazine. But it does show, it talks about Townsend Brown's experiment. That was in 1922, as he was close to a senior in high school. And back then, by the way, I think the 10th grade is what people went up to. They didn't have 12 grades in high school then. But he was featured in that. He won several science contests. After he graduated, he tried to go to University of Southern Cal. And he tried to present his ideas to one, the Nobel laureate, Dr. Millikan, who had done some work in cosmology, I guess is the field it was. But he ran into opposition because since his ideas were different, Dr. Millikan just kind of dissuaded him, that he told him that his ideas would never work. He needed to go back to school and learn more about science. Townsend Brown, being disappointed, went back to Zanesville, where he had come from, and then enrolled into Denison University. There's a big controversy about this now because he says, by his claims, that Dr. Paul Biefeld became interested in his experiment and encouraged him to do more experiments, and eventually it became known as the Biefeld-Brown effect. In today's literature today, people have gone back to that university and they can't find anything on Townsend Brown. Al Throckmorton, Colonel Al Throckmorton of the U.S. Air Force, he was a member of the Tesla Tech. He was a member, told me this. He said that he went back right at the after he had heard about the stealth bomber and its development, and went back to Denison University because he went there. He attended the university under Paul Biefeld, and he said that when he was attending it back in the 40s, that Paul Biefeld talked about the Biefeld-Brown effect. But when he went back to do some investigation later, he said all the material in Townsend Brown had been removed. It's like he didn't exist, which is very common for people being associated with a lot of the, what I call black research programs or things similar to that. In this slide here, in this picture here, you see the FlameJet generator. If you'll notice, it's an asymmetric capacitor. It's a series type capacitor. Each plate is a little different. His kind of goes out like the way a jet engine would go out, and it exhausts. The way I did it was a little bit different from that, but it did still work. Next slide. Yeah, you can pass over. We talked about Townsend Brown's a little bit. This is his laboratory in Zanesville, Ohio, around the 1930s after he had graduated from Denison University. He did get his doctorates there, and for a time he worked at Swayze Laboratory. That was his first job, and then later he went to the U.S. Naval Research Center in Maryland. I have been there. I've seen that laboratory. It was where Michelson-Morley did the Michelson-Morley experiment. I want to say this. You don't go to the Naval Research Center and work on experiments unless you either have a master's or you do have a doctorate's degree. So his second job was there he did some experiments there. He improved on his device. His first patent was 300-311. Go ahead and go to the next slide. Here he is again at Agnew Bonson's laboratories in North Carolina around the 1950s. We'll skip back and forth in this a little bit. This, of course, was later in his life and when he was in his 50s. Next slide. This is also him in a newspaper article. I read this article back in 1972. I kept up with Townsend Brown's life because from the time I was a kid in elementary school, I just followed him. There was the magazine that they had, a little magazine for kids back in the elementary school grade that talked about science. It was a science magazine, and that was the first time I came across Townsend Brown's name. And in there, they were talking about the Avro craft and building a flying saucer-like aircraft in Canada. But they also mentioned him because he had an article in Aviation, I believe it was Rand McNally's Aviation magazine, where he talked about building an aircraft that would go up to 1,000 miles per hour, which even in the 50s, that was fast. That was fast. Next slide. Yeah, here's the asymmetric capacitor. This was patent number 300-311. And any of you people that do Townsend Brown's research, or even any researcher that refers to an asymmetrical capacitor, you need to read this patent because he explains in there how he built this. He had copper plates, and in some cases, I think he even used lead plates, but he had copper, and then he coat these. There was, in this particular one, there was 9 capacitors, and in between these, he used empire cloth. Now, what is empire cloth? Back in the old days, before rubber got synthesized, empire cloth was used on a lot of wires and stuff. It was a cloth made out of wool or cotton, sometimes silk, and then later nylon. But if you go and look at some of these old radios and old circuits, you'll see that that's what they used to wrap it with. But he took this empire cloth. On the outside, he had his first initial contact going in here, and then there was an insulated body of the empire cloth between it, about 1/4 to 3/8 of an inch, roughly. And he had 9 of these plates. And at the end of these plates, he had this little, right here where it says H in the capacitor, was a break. It was like 10 or 11 thousandths of an inch. And what that was, it was to prevent an overcharge where you would discharge a hole in through your plates. But you had each one of these plates, and then you had the end, the negative, as we say in DC, and positive coming out on the AC, or the current voltage would run through there and come out on the other end. And then later, of course, I think there was a picture of it in here. The next slide. Oh, here's a vacuum tube that he made based on the same principle. A being the flow coming in, and then B being the negative coming in, and this was in a vacuum. He ran into a lot of controversy over this. People kept trying to say it was ion wind, and he said, no, it works in a vacuum. Later in his life, in France, he did some tests that showed that it could work in a vacuum. Now, how successful that was, I don't know. I just know that it was successful enough so that in one of his videos, he shows him celebrating with a bottle of champagne. So it must have worked. Next slide. Next slide. I guess. There we go. Here's a mechanical drawing of the plates, the negative going in, and then each one of the plates, and then B, the exit part of the plate. This is British patent 300-311, which was actually his first patent. Next drawing. And these are just different. This is a frontal view of it. And one thing he says in his patent here, he talks about these plates. He also talks about how this particular plate setup could also work in a vacuum. One thing that he did in his patent is he built these tanks full of oil to test it. It was mineral oil, it was a dielectric oil, and he'd run charges through it, and then it would actually move in these. And he did that to show that it was not ion wind. Even to this day, in the field of electrogravitics, you can get on one side, you'll have those that say that it is. You'll have these physicists that say it is. And then you have those on the other side that argue that it's not. It's still controversial even today. Next plate, next drawing. Here's a rounded version of it, a cylindrical version of it. The same thing. You have plates that are in the center. What I did later on, I didn't do it with, I did build these. I did actually build these capacitors in Michigan, and I had tried, I didn't put them on a rotary device, but I did put them on a pendulum device, and you could hit it and it would discharge about 7 degrees. So they did work. Unfortunately, I had a fire in our barn and I lost all of my high voltage equipment. I've had to replace that, and I'm still replacing it. It was a setback, but it was also, I'm glad that I was able to do some of the things I did before the fire. Next drawing. Here is an asymmetric, this is basically a generator built using Townsend Brown's effect, using asymmetric charges with a dielectric between them. Then over here's a motor. He built this, and then he was able to turn a motor with it too. My understanding of this was that these work better than just the regular electrostatic motors. They built up a voltage. They had a dielectric between them, and it actually produced more power. I would like to build these again. I'd like to see you people out there that are younger than me build these too and try this someday. I have seen electrostatic motors on the internet, but people have demonstrated, but I have never seen anybody build a Townsend Brown type asymmetric capacitor, generator, and motor. Next. Here's Townsend Brown using the asymmetric capacitors. This is in his laboratories where he's actually testing them. The way he did it is he had it hanging from the ceiling, and there was a little bearing inside this little box in the middle. He had them balanced, then he'd turn them on, and his power, I guess the power came up from the bottom here and connected to them, and then he'd turn these on and they'd start spinning. What he noticed in this was when he did the test, they would, at different times during the month, especially during the moon cycle, they seemed to increase and decrease in speeds. This was something that he noted in his research. He was very good about logging things, and he noticed that this power that he thought that somehow the gravitational effect of the moon and the earth were affected. The electric static part of the earth was affected by this. So he did make note of that in his notes. Next. Here's the patent 2,949,550, which most people are very familiar with, that he built later in the 50s. He built this, he started, and you'll notice on it in the drawing, by this time he was using stronger dielectrics between the positive and the negative plates. He was using, he had tried different types of dielectrics. Barium titanate was the one that at the end that he was working with, because it was very, very strong, very, very strong dielectric, and he was only using 2 plates. And in this, you'll notice that the negative plate, the positive plate, or actually the negative plate, is bigger than the arcuate electrode that's on the front. So in some of his patents, he talks about a triangular effect where it goes down to a point where how this energy, if you can have a bigger negative effect going to the positive effect, creates a greater motor type force. The project, the Winter Haven project, and the beginning of this project, it was classified, and then eventually they declassified the part of the project. But this was in 1952, in California, where he was at in his laboratory. He worked between the laboratory in California and also in Ohio at this time. He was back and forth. But he was working with the Air Force, and they said at one point in time this apparatus went beyond 37 feet per second. This particular device was 17 feet in diameter, a total of 17 feet in diameter. These disc type capacitors were about 3 feet in diameter, with an arcuate electrode across it that's covered about a third of it. Next slide. Here's some variations of how that would have worked if you were going to build an aircraft. He has the electrode, the positive electrode on the front, and he's showing if you were to build this, you'd want your power supply on the inside, and then your negative side would come out this way, and then your positive side would be in the front, like the way they show it. And this is how it would work in a particular aircraft design. And he called it then an electrokinetic apparatus. This is probably the most famous of all patents, the most I've seen after I built this, I have seen a lot of people on the internet try to build this. Russell Anderson built this. He and I talked about it quite a bit. His were much bigger. They went slower but mine went faster because mine were smaller. My biggest ones that I had were 4.5 inches. And his was, he actually built, I think, 3 feet ones. And when you figured his power supply, his was about the same as mine. His were just going a little bit slower because the capacitors were much bigger and they would spin around. But it was working for him. It worked very good. He got his master thesis on that, I believe. Mine, the first ones I built were actually 1.5 inches in diameter. They were very thin. The next ones I built were 3.5 inches, 4.5 inches, about 4 inches. When I did when we did the documentary back in 1996, those that you see in the background were being powered by 250,000 volts, and those two were about 4 inches in diameter. And Tom Balone and I were working together. Later, he did a presentation, and we turned them on. And the unique thing about it, Brown said you could get them going in reverse, and we were able to get them to go in reverse. It was real unusual. That was the one and only time that we were able to do it. I don't know what we did, but we were able to reverse the flow of the current and get it to work that way too. So that did work. Next slide. Here is a drawing from Thomas Terman in 1971. He had been talking with Townsend Brown about how to build the electrokinetic apparatuses, and this was just some notes from him. He encouraged more of a dome high center in his on the negative side, and then of course the plates, a dielectric coating on the front between the positive discharge. I don't know if it was him, but a story I heard at the University of Phoenix was that somebody had built the original capacitors, the 300, 311, from the British patent, and they demonstrated this as a college experiment. And a week later, this was about the time of the release of the stealth bomber. The university was paid a visit by the FBI or supposedly FBI agents and I guess the men in black, as people would call them, and they came and they confiscated this guy's device. They didn't want the public to know about it at that time. I don't know if any people out there have heard about that, but we can talk about that later. Next slide. Here's a picture of Brown with the 3-foot disc. He's just holding it here. This is roughly in the 50s somewhere, the 1950s. It could have been also at Bonson's laboratory because he did do some experimentation with that later. Next. This is Paul Lavallette's explanation of the Biefeld-Brown effect. He called it the well. It's like you have a high gravity field and a low gravity well. And using in his subquantum kinetics book and Secrets of Antigravity, he has this. He shows 100 kilovolts, the negative, and a negative charge and a positive charge, and it results in the force going this way in the direction of negative to positive. Next. Electrokinetic generator. This is the electrokinetic generator that he patented in about 1962, patent number 3,022,430. This is another drawing. As you'll notice, he went from the patent of 300, 311 in an asymmetric form to this. And I think this is very keen and unique. from a marketing standpoint, I think Brown was trying to get his device into the aerospace industry, and he saw this as a way to do it. I think he knew that jet engines were still kind of new. They'd been around about 8 or 10 years. So what did he do? He says, well, I know I need a large volume of ions produced. And what's a quick and easy way to do that? Well, use a flame, use a jet engine. If you go across these plates and you can produce a large amount of ions extremely fast, and this was a way to do it. And you built up a real large charge at the same time, and this is the way to do it. Next slide. These are just pictures of the plates of how he made them. Mine, later when we get into the picture of my plates, they're a little bit different, but they still worked. His were probably pressed out in some metal. I think these were made out of steel, if I'm correct. I think they were actually pressed out of steel when he built his. Next. This right here this is what I built, and I'll show this later on in my slides. You have your grid, and what he talked about in this particular patent, he wasn't just looking at it as an aviation platform. He was also looking at it as a way to generate electricity. And what you would do is you'd set it, after you had your high voltage source coming out of the jet engine, it would hit a grid or antenna, what I call it, whatever you want, a grid. And then it would come down, and you'd have a series of capacitors of different voltages. And then you could downstep these. And what he said in there is you could pull off of each one of these different voltages and run different power sources off of them. I was able to show that this did work. The problem I ran into was the point, I call it the point system. I'll have to show that later in my drawing. But I think it did work, but I think it could have worked better if I'd had just a little bit more time when I built that. I was about a week and a half out from doing the presentation, so I built stuff pretty fast to get it to work, just to demonstrate this. Next slide. Again, here's how you would apply this. Also, how you could also apply this using a jet stream coming out the back end. And I think in one of his particular drawings, he actually shows a round circular device with 2 jet engines with negative charges blowing out to produce a large amount of negative charges very quickly. Next slide. This is the stealth bomber. It's been controversial as to whether they used Brown's device in it. There, Paul Lavalette, by all of it, said that when he got the information on the stealth bomber back in the early 80s, it was everything that Townsend Brown had said. He said that you would need, he said, I remember 30 million volts of electricity. Can't remember how many kilowatts, but he was talking about a rounded cylindrical type disc in the 50s. And later he said the best way would do this would be with a wing type device. The stealth bomber produces between the two of these engines 70 megawatts of electricity. And it supposedly comes out to be about 30 million volts out of each side. The wingspan of the stealth bomber is about, I think it's 179 feet between here to there, and the length is about 79 feet this way, if I'm not mistaken. But the angles at which Brown talked about are very similar to the angles that they use. On the back end plates of the stealth bomber, there is this is by the engineer's own notes. They have it, they cool the gas as it comes off of there to avoid radar detection. One thing that Townsend Brown found out was that high voltage DC blocks out AC. So it would have been ideal to use for evading radar. Next slide. Here's a picture of the plates. I'm going to start with the initial construction of how I built mine. I used wood to hold these plates together. And these plates were actually from out of they were old computer hard drives that I bought at a surplus store years before. Never did know how I was going to use them. I started building this here in Denison on Bond Street. And later I finished the initial jet engine on off of Main Street where I was living at the time. I had 11, I think it was 11 of these plates, so if you count them. Next plate, next slide. This is from looking down from the beginning. I bought this tin plate at Home Depot, and this is just a picture of it looking at where I tried to get them concentric as possible. Next plate. Here's another shot from the other end looking down toward where the tin plate from the inlet is. This is from the exhaust side. Next picture. Now what I used here on these is I had some old coffee cans and I cut holes in them. I started with about a 1 inch, the next one was 1.25 inches, 1.5 inches, each one of these plates. Instead of making it angled like he did, I did it that way. And then I up to about 3 inches is where these holes was the largest. And that was to form so that when the flame came out, it would go out kind of in an angle. And then the last 3 or 4 plates were 3 inches on the exhaust side. And then I had a nozzle on the exit side that I put later on. That's the one you saw earlier in the video. Next plate, next draw. Here's the blower. I had it enclosed in a coffee can, and if you'll see right back here, it's just an old computer fan that I used. I changed this around quite a bit later when I got in Michigan, but initially I started out this way. I used old Bunsen burners for an old Bunsen burner for the initial gas discharge through here. Down here, I had it fixed down here on the bottom where I could add natural gas and CO2 both, or air if I wanted to. Next drawing. Here's a little bit better, closer look of where I put these in here, the cans in here, then I coated them with aluminum foil a little around them to kind of seal them off. Underneath here, you see underneath it, the power supply was mounted underneath. Next drawing. Here's a closer version, and here's my helper, Dakota River the cat. The curious cat looking at the where I had hooked in. I'd insulated this. I insulated the needle point from the discharge of the gas on purpose so that I wouldn't have it grounding back here so that the spark would go forward. Unfortunately for Dakota River, he didn't have a long life, but he was I just put that in there, just something humorous. Next photo. Now you can see at the back end here that I have the nozzle hooked to it that I made. And I made this nozzle out of, believe it or not, it was for mixing coffee, a coffee drink. And it was made out of stainless steel. I've actually still got that one on my new generator. It was the only thing that survived the fire. And I've got it mounted on the new one. It's right now under construction. Next slide. You can see the nozzle. This is it. You can see the capacitors on each side. There were, I think I had 10. Yeah, I had 10 or 12 of the 20,000 volt capacitors on each side. Now what you're looking at here is known as K-wall. It's a ceramic base. It looks like cotton, but it's a very high temperature. We used to use this in the refining industry. I worked at a copper refinery and I learned how to use this material. We used to set it on top of the launders when the copper was melting, and it wouldn't burn. It had a burning temperature of about 3,500 degrees, I think. This aluminum going across here, or this metal, is where I set the screen later. But this is looking at it from the exhaust side and looking at each one of the plates. Next slide. Here's another drawing of the blower and stuff. I've got it enclosed here. I've got the front plate right here. So and right here you see the ground where you hook your capacitors. You ground all of this, and then it's grounded on the other end as well. Next slide. This is as I'm constructing it. You'll see that what I did here is, when I enclosed this, I used muffler wrap, and I used a real high temperature. It was 3,500 degree temperature epoxy in this to seal off the tube inside. And the muffler wrap was, you just wrapped it around, and you could glue it and seal it. And it worked real good for this because you could run gas through it and it didn't burn. Natural gas usually burns a little bit less than that temperature. So around 1,500, I'm going to say it varies, but if you add a blower to it, but it worked for the experiment that I did later. Next slide. Here's a little bit different picture of it. You can see the capacitors. I've hooked the capacitors up to the plates at this time. And inside here, the high voltage needle that I have it connected to that as it goes through these plates. Next slide. Here's the exhaust on it. Here's the discharge ball. Later, I redid this in Michigan, and when I'd get the discharge off this through here, I had another one going, and I was able to actually get about 3 or 4 inches of a spark off of it once I got all this running. And so I was getting a good high voltage off of it. I could get it out to almost 4 inches, and then I'd lose it, but it worked pretty good. Next. Here's this is off of Main Street here in Denison, Texas. This is just another picture of it, another picture of the discharge ball. And I had this fixed with a screw. You could set this gap to different speeds, which is what you would do if you were going to come off of something. You'd want to pulse it at different, with a DC pulse, you'd want it to pulse at different speeds. Next picture. Again, looking down the inlet all the way to the end of it. And then this is the top part of it. I put K-wool over the top of this, and then I made a cover for it later. Next picture.
Okay, and Larry, I should mention we got probably about 10 minutes left. So
okay, this is in the initial testing of it in Michigan, and you'll see these were just different tests I was running on it. Next picture. I'm going to go through this pretty fast. This is it in the completed state. I sealed these with wax on the capacitors to keep it from arcing over. Next picture. And this is just when I was doing the construction before I did eventually in Michigan I added a regular igniter to it, battery powered igniter to ignite it. Let's go ahead and go on through it. This is just a capacitor setup. I had a whole bunch of these pictures, so go ahead, Tim, if you want to. This is just the inside of this is in Michigan right here when I was redoing it. This is where I did the screen test. Then you can go back to that patent and you'll see the grid that I built for it. All the power is underneath here. This was separate. I built this separate from it connected to the high voltage power system, separate from the generator itself. Next picture. This right here is your point system that I built that would rotate. This rotated roughly about 20,000 RPMs. I wish I'd have had more time to build this. I used plexiglass to build it, but it would spin and it would distribute it was a pulsing effect. And this is what Brown talked about in his patent, where you did this, it would pulse it, and then it would go off into the discharge capacitors from the grid, and you could distribute the voltage that way. Next picture. This is it. The problem I had with that is it wasn't as straight as I would have liked to have built it. These are the capacitors that I used. You don't see the first initial capacitor coming off this are two 20,000 volt capacitors, 40,000 volts. These two were 400, 200, 100, and then the last two actually was about 75 volts. Here's the system underneath. This is where the wires go in and connect to it. And then I stuck these capacitors in line like this. and it came off. I had to build a special meter to measure the voltage, and this is what you're seeing down here. Is you're seeing the meter, and it was a variable. It was variable on the high voltage system that powered this. Next slide. This is all of it underneath. And then, of course, this is just a picture of the Bunsen burner with a nail, small nail that came to a fine point to ionize the gas as it went through it. Now, the gas would come through here and come out here. And I had this mounted so the gas blew out through there, and it would be ionized going into the capacitors. This is just another picture of it. And then here's the grid. And this is it when we were testing it in Michigan. This was just an experiment I did with it separate from that, where I tried to come up with the needle coming out perpendicular to it. There's a capacitor. There's a plexiglass. This was just an experiment. I never did use this, but I have built a new one where I'm using different size plates. I'm just experimenting with that right now. Next slide. That's just a picture of them there in my, right here too. These are readings at different settings off of the capacitors. You're looking at about 136 volts here off of one of the readings, 143 when I was testing the gas going through it, 190. And then this was an amp reading off of the, when I did an amp reading test off the last capacitor from it. This is a voltage reading. On the very last capacitor, I was getting almost 15 volts off of it. And that's all.
Amazing time. We did it. We made it through. We made it through all those slides. So let me do this. Let me take the slideshow down. I'm going to bring everybody in. We got to give you a hand. So this is absolutely amazing. We got some amazing stuff today. Mr. Larry Deavenport. It was 20 years ago at Tesla Tech that I saw that.
It was 2004.
Compelling
Paul
stuff.
Shatskin was there doing the story. I don't know if you ever met him or not. He was writing he did the last biography of Tesla, and it seems from according to him, Tesla, Tom Townsend Brown was much more involved in the black research than we thought. I think, if truth be known, he was probably all the way from the building of the stealth bomber to the end. He was all involved with it all the way.
I've heard that about the stealth bomber.
And I think he was. Yeah. And then when you start looking at all the things that they did later on and they applied it's Brown stuff all the way. And the question is here, if a guy patented all this, who would you go to if you were going to build a plane? You'd go to the guy that had the patent. You'd have him involved from the beginning, all the way from top to bottom.
Well, and what you're saying about the plasma disrupting radar, I mean, I can attest to that. I've seen that, multiple places. So then like people had talked about the B2, supposedly as anti-gravity because of Biefeld-Brown. My thought was that we're using the Biefeld-Brown to disrupt radar and probably using a version of that FlameJet generator. I've thought that for years. So.
Yeah, they do have some on the front of the stealth bomber. They do have radio jamming capabilities and radar jamming capabilities, which is probably different from part of
Yeah.
Townsend Brown's, but that's all classified. I don't know. I've heard how some of those work, but it's pretty amazing. The whole,
yeah. Let me go to Bernie real quick. Bernie has a question,
So-
and then we'll.
I've got a question in regards to the B-2 bomber, and that there's like rumors in the UFO world that there's more to it with the Townsend-Brown effect, that
We just
potentially
answered
it
that one,
takes
Bernie.
it into space, though. Like, do you think there's anything to that, or that like that it was the step between that and the TR3B sort of thing?
I think what you're saying there is probably true. It was a step between the TR3B, which is, they've since come out and said it is a top secret classified plane, I've heard. But it led up to that. I do know that the TR3B, the patents, it uses conventional and non-conventional ways of flying. I heard that the stealth bomber could go faster than what they said it could. That's what Paul Lavalette said. He said that it was capable of going much faster when they kicked on they used conventional engines to get it off the ground, and then they'd turn on, when they got up to high altitude, they'd turn on the Biefeld-Brown effect.
Yeah. Well,
I've got one last question.
Yeah.
Do you think, have you seen much of what they're calling the Graviflyer and the different groups in APEC on that? And do you think that the Brown effect has to do with Alexi's machine, and if it works, that's what it would be?
Well, I know that when James Frank King and Townsend Brown did the research at Agnew Bonson's laboratory, they experimented with rotating AC with DC, and there's a picture in there in one of the videos that shows them testing it, and when they turn it on, it just kind of goes erratic. I think they were trying to see if the AC, what the AC would do is the DC would shun out the AC part, but causing it to become more powerful DC on one side. And I think that's what they were looking at, more of a steering mechanism, I think, than anything. I do know that Stan Deyo wrote a book called The Cosmic Conspiracy in 1977. He worked on the top secret research in Australia out in the middle of the desert somewhere. There's a facility there. That's where their anti-gravity research facility is. And what he described fits perfectly with what they say about the gravity flyer. They're using AC and DC and using sound waves, much like what Tesla would do when he would run.
Yeah.
When he ran
tests. Guys, we're at the top of the hour. I got to move on. So let's give Larry again a big applause. Larry, thank you, sir. Amazing presentation. And I don't mean to rush things too much, but we have a big one coming up from Mr. Alex Wolf. And so what I'm going to do is take everybody out here. And let me see. So now I'm going to put up. Okay, perfect. And I'm going to put this thing in theater mode. I think that is about as good as we will get. Okay, there we go.
Good morning, distinguished guests and fellow seekers of knowledge. Today we embark on an intellectual expedition into the frontier of scientific discovery, navigating the nuanced terrain of unified theories with a bold and meticulous spirit. Now I know what you're thinking. Great. Another physicist trying to sell me on a theory that's supposed to be the next big thing. But bear with me, because we aren't here to peddle snake oil. I am reading off my phone here because this is a lot. This presentation is not about claiming a singular, all-encompassing theory. Instead, it's about exploring one of many unified physics models. testament to the plurality and adaptability of scientific inquiry. We are here to deconstruct and re-represent the complex interplay between quantum mechanics and general relativity, illuminating the path towards a deeper universe. Our goal is not to present a theoretical endeavor, but to prove our framework through real-time, practical demonstrations. We will perform full calculations on screen, deriving tensors and values and integrating them within the unified theory. By the end of this presentation, our aim is to make the complex comprehensible and the theoretical tangible. One of the main questions people have about a theory as advanced as ours is how it can be logically proven and authenticated. This is particularly challenging because physics has become such a convoluted and ephemeral subject that verifying a theory like this is sometimes looked at like some sort of mystical artifact and not a thing that can be approached scientifically. However, it is not a mystical artifact. It is not something unachievable. It's a strict process of verification and authentication, which can be self-contained, self-verifying, and utilizing the scientific method. In this way, what we're about to do in this presentation has never been done before, at least not to my knowledge. The whole point of our presentation is to break down this very question about how a unified theory would even be verified or authenticated using clear, logical steps. We're going to perform demonstrations of some of these authentications. Let's go through some. Firstly, our theory achieves mathematical consistency, meaning all its components fit together, no contradictions. Secondly, we compare our theoretical predictions with results from high-energy experiments like those conducted at the Large Hadron Collider, validating this framework against things like Higgs boson data. Thirdly, we align our theory with standard experiments and existing models, ensuring it fits within the broader scientific network and framework. By matching our theoretical outcomes with experimental data and existing theories, we demonstrate the viability and the accuracy of our work. The difficulty and significance of our endeavor lie in not only addressing how such a complex theory can be authenticated using the scientific method, but also in breaking down and verifying these ideas in real time. This makes our approach both innovative and rigorous, bringing clarity to a field that often seems obscure and impenetrable. In addition, we will cover masses of information, blueprints, calculation, and technical usages of the unified theory. This isn't just about high-level theory. It's about practical applications for personal and professional development. We're going to span multiple disciplines and show exact results with instructions for repeatability of this research and these experiments: physics, engineering, computing, chemistry, even genetics, even defense, and beyond all, connecting and circling back to the potential of alternative energy. The goal here being to deconstruct and re-represent these complex, often ephemeral seeming ideas in such a way that, if I have hopefully done my job correctly, that is, that utilizing these theories for practical use immediately after viewing this presentation for R&D and personal benefit should be easily achievable by anyone who has viewed this presentation. And to start, in our era of rapid technological advancement, breakthroughs are often the result of cumulative, collaborative efforts rather than isolated genius. Our journey today is made possible by the convergence of expertise from diverse fields, including PhDs, NASA alumni, and pioneers in computational science. This collective effort underscores the collaborative nature of modern scientific progress. We acknowledge the trepidation that often accompanies such ambitious presentations. Therefore, we emphasize humility and collaboration, framing this work as an ongoing collective effort. This approach bypasses preconceived notions of the ego and assures that the focus remains on the science itself. Historically, singular theories like Einstein's achieved rapid acceptance. However, today's diversified and decentralized communication network makes such swift, unilateral acceptance very unlikely. Instead, we embrace a dynamic landscape of theories, each contributing to the mosaic of scientific understanding, but focusing on one. To illustrate this point, consider the Beatles. Much like Einstein's theories, their music transcended cultural and geographic boundaries, gaining widespread acceptance and acclaim. The Beatles didn't just create songs, they revolutionized the music industry in a statistically verifiable way, blending diverse influences into a cohesive and groundbreaking style. The statistical part, their rapid rise to global fame, can be attributed to a relatively centralized media landscape and the novelty of their sound, still making them one of the most, I think, the most profitable musicians of all time. Statistically irrepeatable. However, in today's world, the landscape of music and scientific ideas has fundamentally changed. The internet and social media have fragmented our channels of communication, making it less likely for a single theory in science or even a musical artist to dominate the public consciousness, much like the Beatles did, but also much like Einstein did in the 40s and beyond. This decentralization means that while the acceptance of any new theory, such as a unified physics model, might not be as rapid or universal, it allows for a richer, more diverse exploration of ideas. Our exploration is not an attempt to unveil a singular, all-encompassing truth, but rather to highlight one of many unified physics models, the ones that actually functionally work. This approach acknowledges the collaborative and evolving nature of modern scientific discovery, recognizing that breakthroughs arise from the cumulative efforts of many. We reject the outdated notion of zero-sum thinking, the belief that there is only one definitive theory. Instead, we embrace a nuanced understanding, celebrating the robustness and adaptability of multiple models. The paradigm shift underscores the strength of scientific inquiry in its ability to evolve and adapt. Our journey today is made possible by the collective expertise and technological advancements of our time. This is a testament to interdisciplinary collaboration and innovation that drive contemporary science. It's not the work of isolated geniuses, but the result of a community of minds pushing the boundaries of what is possible. Throughout this presentation, we will delve into a groundbreaking framework that integrates quantum measurements into the curvature calculations of general relativity in a unique way. This innovative approach navigates the complexities of observation and measurement, harnessing the Born rule to forge new mathematical pathways. The goal here, as I've said, is to deconstruct and re-represent these complex, often ephemeral-seeming ideas in such a way that if I've done my job correctly, utilizing these theories practically and immediately, as I said, for personal benefit should be easily achievable. We're going to break down the history, the qualifications, and the technical and mathematical aspects of what something actually needs to be required or considered or authenticated as a theory of everything, grand unified theory. We're going to take these ideas, deconstruct them, examine them, and then these ideas, the history of why this theory has been so evasive, it will be addressed. Then we will authenticate the theory. By doing so, we can begin to break down this seemingly endless and continually more abstract problem of how something can be accepted as a unified theory with fresh eyes. We can break down and understand what the complicated and exact technical and mathematical as well as historical standards of theory would need to be meeting to be considered this. And we can also address these problems and assure the viewer understands them and the evidence for unified theory with those fresh eyes. AI and the convergence of exponentially advancing theories provide a unique opportunity that has only become available in the past few years. This convergence allows us to perform advanced calculations in R&D, previously accessible only to advanced supercomputers, by leveraging cloud-based computing. But for anybody who's just starting out with science here, that's a mouthful. So let's start small and not get ahead of ourselves. Mathematics in its purest form remains a theoretical tool, an abstract narrative. But when anchored by empirical data, it transforms into a powerful instrument that elucidates the mysteries of our universe. Our theory deconstructs simplistic notions, showing the concept like lines or points or really anything without measurement units are mere abstractions. We will rigorously derive tensors and values from general relativity and quantum mechanics, integrating them then to demonstrate the robustness of our model. Going to do them separately and then show them integrated all at once in a full calculation. Plus some other authentications. We'll match it up with the Higgs boson data. Now, let's take a moment to reflect on the profound advancements science has made. Now, picture the Voyager record. A golden disk sent into the void, carrying with it the echoes of human culture and the haunting strains of a sad blues song. A song made by a slave. These things were included to represent the pain of humanity. This was a craft sent into space. It's going to far outlive human beings. It's going to be the only thing that survives or lasts when humans are long gone. Carl Sagan talked about this in depth. And it's quite profound to think of the scientific advancements we've made now that aren't even included. Yet, despite all the triumphs of science, human suffering and existential trepidations persist, often outpacing the solutions science can provide. The human condition is marked by suffering, and it is the ultimate aim of science, I believe, to alleviate this. Any good scientist should think that. This unified theory, while deeply technical and measurable, holds the potential to address some of these fundamental and ephemeral human challenges, offering a new lens through which we might understand and alleviate suffering. The endeavor that we're about to embark on here is profound, eerie, and sobering. These mathematical constructs we explore today may far outlive human beings or something far greater, enduring as testaments to our quest for understanding. We span vast scales of time, dwarfing the fleeting existence of humanity and our struggles. It is this vast perspective that underscores the need for such a theory and necessitates a shift in our thinking. As we embark on this journey together, I invite you to engage deeply with these ideas, to question, to explore. Let's deconstruct these complex theories and let's reassemble them into a coherent and accessible understanding from the ground up. Together, we will push the boundaries of knowledge. What we know, and we will venture into new territories. Now we'll move on to section 2 here. Eyes of your eyes. Mitigating problems between quantum physics and general relativity. To grasp the challenge of unifying quantum mechanics and general relativity from the ground up, we must first step back and understand the historical contexts and fundamental principles of these two pillars of modern physics. In 1915, Albert Einstein revolutionized our understanding of gravity with his general theory of relativity. He proposed that gravity is not a force, but a curvature of space-time, caused by mass and energy. Now, the elegance of this theory lies in its description of second-rank tensors. Essentially, that's where the uniqueness came in, I believe. Encapsulating the geometric properties of space-time within these second-rank tensors. Imagine a heavy object on a stretched rubber sheet. That image a lot of people have seen. Causing the sheet to curve, of course. This curvature directs the path of smaller objects rolling around the sheet, much like how planets orbit the sun. Now, I'm going to move on here to quantum mechanics. I'm going to explain a little bit about that. In the early 20th century, quantum mechanics emerged, providing a framework for understanding the behavior of particles at microscopic scales. Unlike the deterministic nature of GR, quantum mechanics introduced probability, uncertainty through wave functions, encapsulated in the famous Schrödinger equation. And we're going to show a little example here. Very simple. Imagine a dotted line. Imagine another line that's solid. The dotted line is here, and the solid line is here. That's essentially a good example of how particles can exhibit both particle properties and wavelength properties on the quantum scale. So these particles, depending on how or why you're measuring them or looking at them, can either be a wave, like a radio wave, or it can be a particle, a physical thing, a photon. Well, there's some argument about whether that's a physical thing, but we won't get into that. This challenged the classical notions of certainty and predictability. Interestingly enough, quantum mechanics and its popularity emerging far before this. The beauty and utility of both theories are undeniable. Yet they fundamentally clash. General relativity excels at describing the large-scale structure of the universe, while quantum mechanics explains the behavior of particles at the small scale. However, when we try to merge these frameworks, particularly in extreme environments like black holes or the early universe, their equations yield nonsensical results or completely unintegratable results. To illustrate this conflict and the role of second-rank tensors, which we'll explain here, second-rank tensors, I'll say that more clearly. To illustrate this conflict and the role of second-rank tensors, consider this metaphor. Imagine scaffolding, holding up a building. Second-rank tensors, such as the metric tensor and general relativity, act like this scaffolding, supporting the structure of space-time and holding up the reality we experience. Now let's try another metaphor to really drive the point home. The metaphor eyes of your eyes for second-rank tensors is quite poetic and metaphorical. It suggests that just as our eyes allow us to perceive and understand the world around us, second-rank tensors in the context of general relativity provide a framework or a structure that helps us perceive and comprehend reality. The reality of space-time. In the realm of general relativity, second-rank tensors can be likened to the eyes of your eyes. Ergo, they serve as framework that allows us to perceive and understand the complex fabric of space-time. As similar to how our eyes enable us to see and make sense of our surroundings, second-rank tensors provide the structural foundation that underpins our observations and calculations in the gravitational universe. Just as our eyes gather visual information and translate it into comprehensible data for our brains, second-rank tensors gather the gravitational field's information and translate it into a mathematical formulation that describes the curvature of space-time. The scaffolding of tensors, meticulously crafted through mathematical rigor and computational precision, forms the very eyes through which we view and explore the universe, governed by general relativity. Understanding and utilizing second-rank tensors in unified theories is not merely about constructing theoretical frameworks. It's about equipping ourselves with the tools to navigate and comprehend the profound mysteries of the universe for scientific or personal benefit. By integrating quantum measurements into these tensors, we extend our vision, enabling us to probe deeper into the quantum realm while maintaining the integrity of our gravitational understanding simultaneously. This is what the unified theory we will be discussing and authenticating here today does, in a unique way. Thus, second-rank tensors serve as the eyes of your eyes in this case, and especially in general relativity, offering us a structured view into the depths of space-time's reality, and paving the way for deeper insights and discoveries in the pursuit of unified theories and how they may benefit us. Unified theories, such as the one proposed here, are not merely an academic exercise. They hold the promise of a deeper understanding of the universe and practical applications in technology, energy, and beyond. We will talk about this. More specifically, we will focus on energy later. And it's immediately practically useful. As soon as one understands concepts within this presentation, they can start to peel back layers. Now, equipped with this foundational understanding, we can move on to some of the more technical sections. We'll explore how the unified theory and associated theories solve these problems in a uniquely complicated yet elegant way. By deconstructing these ideas, we aim to make them accessible and practical, ensuring that anyone viewing this presentation can utilize these theories for immediate R&D and personal benefit. And I do believe, and it is my educated opinion, that there is a large amount of unified theories that are possible, that all follow the same basic principles, and all have the same standard staples. We're going to go through that a little later. But for now, let's just get on to the next section. We are walking a tightrope here. I want to make sure that we provide the technical information for the people who are familiar with science, but I also want to make it accessible, as I said, and break these ideas down for people who are laymen's or just seeing this, no prior interest in science. I think this is a logical way to ramp up to more technical data, so I'm not just dropping people in. So, we're going to explain some simple things here before we get to the authentications. The authentications which provide a critical anchor, assuring that this theory does indeed actually, in reality, mitigate the disparities between general relativity and quantum mechanics. We're going to go through the Higgs boson data and compare it against our framework in a unique way. We're going to authenticate it, as I said, in a unique way by deriving the field equations of general relativity, doing a similar thing for quantum mechanics, and then showing them integrated in the same equation, in the same calculation. We're going to show those separately and then integrated. We're going to pair that with all the other types of authentication we have: experimental, computational, and mathematical. But before we get to that, some critical information. So, this is quite the crude drawing, but it's got the spirit it'll work. I find that crappy drawings and writing sometimes help convey the idea best. So, some prerequisite information. What we have here. Can you see that? We want to start familiarizing ourselves so I don't just drop you into this equation. Pay close attention to these here. Any of these characters. These are the quantum components featured in the unified theory. Before we view the whole thing, I just want to familiarize one with these ideas so that they can be aware of what they're looking at with this incredibly complex and elegant equation. So, what we have here is the quantum aspects of this equation, the wave functions, the uncertainty we spoke of. And I'll explain this later, but that's by incorporating something called the Born rule. And again, this is before I show the full form of the equation. You will recognize some of these elements. What I'm showing here is this is how the equation essentially functions. The quantum components are fed into the modified stress energy tensor. Now, the stress energy tensor, for the simplistic and most simplified explanation of this, is kind of representative of the energy in the universe. There's more to it than that, but for the sake of brevity, We'll elaborate more on that later. And as you can see, this is how the equation functions. The quantum components are then embedded into the modified stress energy tensor. Now, here we have the stress energy tensor. That's a pretty typical form for that to be in general relativity. That one I'd say is a pretty typical form for a thing you may see in quantum mechanics, just as the most basic example. And here we have a vector. This equation features 4 vectors, I believe. And it's all the constants that affect gravity. And those are the only ones given these unique units: x, y, z, t. 3 spatial, 1 time, embedded into every single calculation. Or, if you were doing something else, you could use these to represent different things you wanted to correlate or show interval between any of the vectors. Now we're going to move on. You'll see it as modified stress energy tensor. As we talked about the scaffolding, the eyes of your eyes, this is a more visual representation. The quantum components are embedded. They flow into the modified stress energy tensor. And beyond that, they then flow, now that we've accounted for the energy, into the modified Einstein tensor. This is more focused on the matter. And now we have the Einstein tensor. We have the matter. We have the energy. We have the quantum components embedded. They all feed and flow, almost as if energy feeds into matter and flow does. Now, what we have here on the bottom, G underscore I, J. That's the resulting space-time curvature. That's the whole enchilada right there. This equation has a vector which looks like this. And this vector represents an object's position in space-time while accounting for quantum mechanics and general relativity. So the whole enchilada I spoke of, the equation, it all ends up here. And we'll go through that. We're going to review this equation now. I'm going to point out the components. I do want to say here, I would focus again on just looking at these. You'll be surprised when you look at the equation. Now, you don't have to know everything they mean. If you're not familiar, if you are, well then you know what's up, but just look at them. G underscore IJ. You have a probability with a similar thing, underscore IJ. And now we're going to go over this equation. We're going to actually look at it. Oh, hey. Don't worry, it's just a tobacco cigar. And I spontaneously shaved. Sometimes when I'm dealing with these advanced physics things, it helps to have a cigar. Now, we have a foundational understanding of all these really advanced concepts in quantum physics and general relativity. I'm sorry for some of you who are more advanced and we aren't getting to that data. We're getting to the Feynman loops and the authentications and the computation. Just bear with me. Now, we will show for the first time here the full form of a specific unified theory equation. Let that sit for a second. So that's what it looks like. Can we notice the pitchforks? Can we notice the elements of general relativity, our Gij? And that's a very informal and unprofessional way to phrase it, but it does help visually. And for those of us who are advanced scientists, we got to remember people who have no concept of these things yet. Now, we're going to go over this equation, and then we're going to slowly detail what makes it unique. I'm looking at my notes because there's a lot here. First, I'll go over some foundational elements of the components, and then I'll go over some of the elements of what makes them special. I'm going to describe these in very simple terms first. So first we have our output vector. Oh. X, Y, Z, T. It describes the position and time in 4D spacetime. We have our matrix operator. It maps the input to the output vectors. It transforms the spacetime coordinates. Then we have our Einstein tensor. This is the G, IJ, capital G. It encodes the spacetime curvature. We have the stress energy tensor. This describes the matter and energy distribution of the system. Then we have our metric tensor. This is a little g, Gij. This describes distances in spacetime. We have our dark matter and dark energy components. These account for dark matter and dark energy. I know you're thinking, but we'll get to that. We have our wave function. It describes particle state probabilities. We have our Laplace operator. It represents spatial distribution and uncertainties. Then we have the traditional mass acceleration. It incorporates the dynamics of particles. You got the good old MA. Then you have our vector with more spacetime components. Just like the dark matter and dark energy were a vector. All the gravity affecting constants get their own vector with spacetime coordinates and a time coordinate, 4 dimensions. Other than light, we're going to go over that a little bit and explain why. So here, now I'll go over a little bit of some details of what makes this a unique formulation. We'll go over really quick, in a little bit more detail now, some components of the equation. So the output vector, O. It describes the position and time of objects in a 4D spacetime framework. This is crucial for unifying quantum mechanics and general relativity, providing a coherent description of reality at all scales. Branching wave function. This incorporates the Born law. And I'll probably have a voiceover or something talking about that a little bit. It also incorporates the Everett interpretation, many worlds theory. And it's essential for dealing with quantum states and probabilistic outcomes. It addresses the quantum measurement problem. The matrix operator, M. It maps the input vectors, initial states, to output vectors, final states. It represents transformations in spacetime. It considers both real and imaginary components, and I think that's quite amazing mathematically. Two things at odds. We have the Einstein tensor. It represents the curvature of spacetime caused by mass and energy, and it integrates seamlessly with quantum mechanical properties, connecting the geometry of spacetime with quantum phenomena. We have our dark matter and dark energy vectors. We will have a section on this soon, but to touch on this a little bit, they modify the tensors to account for the mysterious components of the universe. It allows the theory to encompass the entire observable universe and beyond, providing a more complete picture of cosmic evolution. We have our wave function. It describes the quantum states and their spatial distributions. It connects to Heisenberg's uncertainty principle, showing the relationship between position and momentum uncertainties that were introduced by those improbabilities we talked about earlier. Quantum mechanical aspects. We have our mass and acceleration components, M and A. They introduce the dynamics of particles, and this links it to the classical mechanics framework within the quantum framework. We have our electromagnetics interaction vector. It integrates electromagnetism, reinforcing its fundamental role in the theory. Now that we've gone over all of the details of this equation and we're equipped to understand it, I am really quick here going to show some very basic information about how you would start to understand from a scientific perspective how these theories would be authenticated. Now, you will see citations and stuff. This is kind of based off of the standards of how one can approach these type of authentications logically. It can be broken down in a manner which really addresses the scientific method, which is what we'll be doing here today. If you'll take a look at what's on the screen here, this is the basic scheme of what we'll be utilizing the methods to assure that every single aspect of the dichotomies of how people would authenticate a theory, for example, quantized versus non-quantized, the most simple, addressing these simultaneously. So we're going to talk now a little bit about the dichotomies present in physics. These are the things that have caused people to argue endlessly from the perspective of an academic or a researcher about what exactly constitutes a token. There's a lot of verbal conversations about things which contradict each other. You can't have one and have the other. It just doesn't work. That makes the theory non-functional. But this is discrediting the fact that theories are authenticatable at a baseline mathematical level, where verbal language is just not going to cut it. Let's talk about some of these. Wave-particle duality, the problem. The dual nature of light and particles. Okay, so this equation solves that by representing light as both a wave and a photon. I'll include some information here, because we did find out when running Feynman loops that the corrective term, which might sound like a mouthful until we've explained that soon to those of us who aren't scientists, which we will, the corrective term gets lower the second you account for light as both a wave and a particle. The second rank tensors, the eyes of your eyes. One of those problems, one of those dichotomies and contradictions people will speak about endlessly. Multi-directional interactions. That's the problem. The solution is to use second-rank tensors for accurate modeling. Quantized versus non-quantized. The problem. Discrete quantum states versus continuous spacetime. The solution, in this specific example, it incorporates both quantized and continuous elements simultaneously. Scalar versus dimension. Problem. Simplifying complex multi-directional properties. The solution here? Scalars for simple properties, tensors for complex interactions. 5 relativistic calculations. Problem. The compatibility of quantum mechanics and relativity. Solution? Embed quantum calculations into the curvature calculations, as we discussed. Now, we're going to explain a little bit about the dynamic nature of the vectors for dark matter, dark energy, and some of the things which make this equation uniquely functional, as well as similar equations and frameworks, so we can start to identify the principles which need to be met. Consider something a unified theory. Okay. First, we're going to talk about the modular nature of the vectors for dark matter and dark energy, and how this makes this uniquely functional. I'll include a little bit of the math down below. And I figured the best way to do this is to just explain these things in simple terms while the mathematics are shown on screen. If you want to pause it, or if anybody ever wants to challenge the math, if anybody ever wants to take the math upon themselves, they can do it in this way. Pause the presentation, and you should be able to see that stuff down here. So, again, sorry for the informal nature, but we will be talking about the dark matter and dark energy vectors, with the 3 spatial and 1 time component. One thing which makes this uniquely functional and has resulted in the lowering of the corrective term when calculating Feynman loops is directly accounting for this. This allows it to basically update the theory with new scientific data without altering the fundamental structure. So, a little bit about that. Let me pull this up here in my notes. And before we get on to the next section, which is going to be a little bit more technical, and we're going to start detailing some of the authentications, I do not believe that you can prove a theory, but I believe you can substantiate it with as much evidence as possible, and that's what we're attempting to do here to the best of our ability. That's the best anyone in physics can offer. But I wanted to address 2 more dichotomies that are approached uniquely by our framework here. And I did want to reiterate that we will be going over other frameworks from other doctors, physicists, and researchers, and showing some brief information about how we assess those as well. But for our theory specifically, I wanted to address supersymmetry. The theory integrates supersymmetric partners to solve the hierarchy problem by balancing contributions to particle masses, particularly the Higgs boson, thus unifying interactions at high energy scales. I wanted to address the geometric foundation in terms of dichotomies as we discussed previously. The theory's use of geometry echoes Einstein's vision of a unified field, highlighting the interconnectedness of all forces. Now, we're going to get on to the detailed analysis and verification of the Feynman loop corrections. That's probably making some of the more advanced scientists out there drool. We're going to go over a little bit of just basic info about this for the lay people here, and then we're going to get to the data. The data will be shown on screen as I speak about this. So, in theoretical physics, especially in quantum field theories and string theory, loop corrections are essential for refining our understanding of particle interactions. These are mathematical processes. Loop corrections account for the quantum fluctuations that occur at various interaction points, fundamentally altering the initial predictions made by a framework by classical or tree-level calculations. Let's talk about a little bit of what these loops entail, why the loop corrections matter. Loop corrections are crucial for the process of renormalization. And when we talk about how somebody can approach authenticating the unified theory in a way which is in line with physics and mathematics with respect to the history and rigorous nature of that. But loop corrections are crucial for the process of renormalization, which allows physicists to deal with infinities that appear in calculations. By incorporating loop corrections, we can make a sense of these infinities and obtain finite and meaningful results. As far as precision predictions go, high-order loop corrections, e.g. 2 loops, improve the precision of theoretical predictions. This precision is vital for comparing the theory with experimental results, which we'll also be doing here with the Higgs boson data and the Reimann solution data, and thereby validates or refutes theoretical models. I think that evidence and experimentation do definitely supersede needing acceptance from peer review or anything like that. I do believe in peer review as a crucially important part of science. And then as far as quantum gravity and unification go, Feynman loops are uniquely developed to address these sort of problems we've been discussing here today. In theories like string theory and loop quantum gravity, loop corrections help in understanding how gravity behaves at quantum scales. And in terms of Feynman loops and authenticating theories, as far as quantum gravity and unification go, in theories like string theory and loop quantum gravity, loop corrections help in understanding how gravity behaves at quantum scales, which is necessary for developing a unified theory that integrates all of the fundamental forces. So here, the bar plot generated by the code visually represents the magnitude of loop corrections for different theories. Generally, you want a lower corrective term. That means it's more functional, more stable. This comparison allows us to see how each theory deals with quantum corrections, shedding light on their relative strengths and weaknesses. Here we took loop quantum gravity, a popular unified theory, string theory, another one, and our unified theory model that we're going over here. And we'll go over some more that are unique and newer from eminent scientists who are pushing the envelope now. So, to kind of explain this accessibly for the lay people first, imagine you have a rough sketch of a landscape. That rough sketch is your initial theory. To get a more detailed and accurate picture, you add layers of shading and texture, the loop corrections. Those layers represent tiny adjustments based on how light and shadow interact, the quantum fluctuations in this example, in different parts of the landscape. Why do these adjustments matter in laypeople terms? Just like adding more detail to a sketch makes it look more realistic, adding loop corrections make our predictions about the universe more accurate. As for fixing errors, sometimes initial sketches have parts that don't make sense or have errors. Loop corrections help fix and smooth these out, especially the little inconsistencies. As for understanding the smallest parts, in this metaphor, to understand the most fundamental parts of the universe, like how gravity works at the tiniest scales, we need these little detailed adjustments to get the bigger picture more clearly. The bar plot we create helps us compare different theories by showing how much each correction one needs. The bar plot we create helps us compare different theories by showing us how much correction each one needs. It's like comparing different detailed sketches to see which one matches the real landscape the best. And how does this contribute to verifying our unified theories? To verify unified theories, we must ensure they match experimental data, which we'll be going over here today, and make accurate predictions about fundamental forces and particles. So here we'll be utilizing the Reimann solution and Higgs boson data derived from CERN repositories to that end. Loop corrections play a critical role in this verification process. And when we showed that authentication scheme earlier, that's where it fits in. By providing detailed predictions about unified theories, providing detailed predictions. Unified theories often predict new particles or interactions. Loop corrections refine these predictions, making them precise enough to test experimentally. Ensuring consistency. By incorporating ensuring consistency. By incorporating loop corrections, we check the consistency of the theory across different energy scales and interactions. This consistency is essential for a theory to be considered a valid unification of fundamental forces. 3. Highlighting differences and similarities. Comparing loop corrections across different theories, as shown in our bar plots, helps identify which theories are more likely to unify gravity with other forces based on their predictive power and consistency with known physics. And in summary, analyzing loop corrections is like adding fine details to a sketch to make sure it's accurate. For physicists, these corrections are essential for refining theories and ensuring that they match the intricate details of our universe. By comparing these corrections across different theories, we move closer to verifying a complete theory of everything. A theory that could explain all fundamental forces in particles. This rigorous process of verification makes the idea of unified theories more concrete and less ephemeral, advancing our understanding of the cosmos. So really quickly, before our next section, going over the experimental results, I wanted to talk about something we found in the data. I thought it was an error at first because when we were running the Feynman loops and the corrective terms, they kept coming out pretty much exactly the same for loop quantum gravity and the main theory we're going over here today. So I kept updating the computation, I kept updating the quantum codes, I kept updating my own hand calculations and what I was having other people look at and do their calculations on. And I had a colleague basically point out some stuff to me that I thought was interesting. It wasn't an error. So we're going to kind of examine the similarities between our unified theory and loop quantum gravity to support what I said. A range of possible unified theories to combat zero-sum thinking. We're going to focus on loop quantum gravity and our unified theory and their principles, calculation processes, and the results obtained from our Feynman loop corrections, which were authenticated in multiple points, like I said. The observation that both theories yield similar results at low loop orders raises the question, is this similarity an error or a reflection of shared underlying principles? Well, definitely the second one. So, LGQ posits that spacetime is quantized at the Planck scale, represented by a network of finite loops called spin networks. These were accounted for in the computations. These spin networks evolve over time, forming spin foams that represent the quantum state of the gravitational field. LGQ is background independent, meaning it defines spacetime intrinsically from within theory, unlike traditional quantum field theories that rely on fixed background spacetime. The theory quantizes areas and volumes, leading to a discrete structure of spacetime, and then for the principles that ended up having the same corrected terms and why that's the case for our unified theory. The integration of light as a wave and a particle in these computational processes, the unified theory incorporates the dual nature of light, treating it as both a wave and a particle as we talked about. This is accounted for in the computations. The dynamic and modular vectors, but especially dark matter and dark energy, allowing for their evolution with new scientific discoveries was crucial in this, and especially maintaining the calculation of the extremely low loop levels, or the corrective terms for low loop levels. The embedded quantum calculations, these all kind of contributed to that. So, this section we're going to break down the Python code and the process used a little bit. We define the constants and functions for the Feynman loop, or loops rather. We define the theories. Separate functions are created for each theory, incorporating their specific principles and calculating corrections accordingly. All this information is included for recreatability purposes. We set the parameters in calculating corrections. This was in code, both quantum code and normal, just classical Python code. We created a comparison table and plotting results. And then we kind of just, we got that, we compared them. And also we did our own hand calculations and had different researchers, as I said, and stuff, kind of verify those results on their own end, amalgamate what everybody's contributions are and their opinions and how those calculations be done, and in the spirit of that being a collaborative effort. So both loop quantum gravity and our unified theory yield similar results at low loop corrections due to their foundational principles being similar, supporting the point and substantiating my claims. Both theories involve quantizing spacetime. The LGQ does this through spin networks, while the unified theory integrates quantum calculations within curvature. Both theories do not rely on a fixed spacetime background, allowing for dynamic and modular approaches to modeling the universe. This is how we can get closer and closer to finding the theory of everything, by isolating these things that make the corrective terms lower with these other authentication methods. The discrete natures were similar. LGQ, or LQG, loop quantum gravity explicitly quantizes areas and volumes, while the unified theory uses dynamic vectors for dark matter and dark energy, resulting in similar quantization effects. So several factors contribute to the similarity here, and I'll go over these quick for the more advanced scientists here. The code uses simplified loop correction formulas. So I think it's been demonstrated here. Some interesting things that I wanted to touch on more, which I wasn't planning on at the beginning, which is that it's not just the main model we're looking at here is not just unifying quantum mechanics and general relativity, but also a myriad of other things we're working in, loop quantum gravity and string theory. And that's proven by the corrective terms and that logical assessment of mathematical authentication we just went through. Let's go through some aspects of the integration. So the nesting structure and nonlinearity of the TOE. The nesting structure, where quantum components modify the stress energy tensor, which in turn affects the Einstein tensor and thus the curvature of spacetime, is a key aspect of this. The linear approach reflects the nonlinear nature of both loop quantum gravity and aspects of string theory simultaneously, while also doing pretty well the quantum mechanical and general relativity aspects. In string theory, so for the quantum components, in string theory, these particles are viewed as different vibrational states of strings, and these vibrations can be thought of as modulating the spacetime fabric. The use of this here, quantum term, and this quantum term with the B vector, could be seen as analogous to quantum state descriptions in string theory and utilized to this end, but applied to a tensorial framework. This kind of proves that this main theory we're looking at here is extremely modular and will create valid computational results in almost any sense. You can account for multiple frameworks at once, or just one. So the modified stress energy tensor and operators for dark matter and dark energy. In loop quantum gravity, the stress energy tensor and spacetime are quantized at discrete levels. The modifications, Tij, dE, Gij, as well as the dm vector, in the theory, reflect the discrete and dynamic nature by introducing variables that account for the quantum fluctuations and corrections at different scales, akin to loop quantum gravity's granularity of spacetime, which was directly worked in. Both string theory and loop quantum gravity seek to explain the curvature of spacetime through their frameworks. In string theory, extra dimensions and brane world scenarios lead to modifications in the Einstein field equations. Sound familiar? While in loop quantum gravity, the spin networks and spin foams result in a granular structure of spacetime. But our approach modifies the Einstein tensor with dark matter and dark energy operators, which is able to reflect the influences of higher dimensional effects from string theory and discrete spacetime from LGQ, while also accounting for quantum mechanics and general relativity in a mathematically and computationally meaningful way. And that's the main point here. But I did have something else to say about string theory. I don't want to get too much into this because there's not a whole lot of time. But the quantum fields in our theory could represent and can represent and model the modes of strings in string theory, which influence the stress energy tensor and the spacetime curvature, similar to how different strings influence the effective field equations and vibrations in quantum fields. We don't have a whole lot of time here, but the quantum aspects in our equation can and also do represent vibrational modes of strings too, on top of things we talked about. Influencing the stress energy tensor and the spacetime curvature, similar to how different string states influence the effective field equations in string theory, which makes it compatible. You can directly implement that. As far as brane world scenarios go, the idea that our universe could be a 3-brane embedded in a higher dimensional space is mirrored in the modifications of the stress energy tensor, and that's brane B-R-A-N-E, not B-R-A-I-N. I know that could be confusing. So the operators for dark matter and dark energy can reflect the interactions between the brain and the bulk. That's for the more advanced scientists out there, but if you want to look into that one, it's quite interesting in calculations. Conclusion. The observed similarities between loop quantum gravity and our unified theory were like really validating in the purpose of this presentation. The similarity between them at low loop corrections levels are not necessarily errors, but reflect shared foundational principles. Further refinement and detailed consideration of higher order effects are necessary to fully understand the differences and validate the theories. We've done this to a degree, but if anybody out there wants to, I would appreciate that. It's kind of the whole point of the science, is to hope that people build on it and validate, invalidate. For future steps, somebody could implement high-order calculate loop corrections to capture more detailed quantum effects. Use more sophisticated models and correction formulas tailored to each theory, which we did. We did that pretty extremely, but somebody could do that even more. Or we will, later. These are just future steps for any other researchers who want to do a peer review, or us in the future when we're researching. And you know, the experimental validation, like we're doing, compare theoretical predictions with experimental data to validate the accuracy and applicability of each theory. So, in essence, the comprehensive analysis and computational verification here in the process of authentication underscore the robustness and consistency of both loop quantum gravity and unified theory, providing a clear path forward for further research and exploration. And we'll go over a little bit about similarities and about how this theory relates to string theory and loop quantum gravity, and then we will move on to the experimental results. The unified theory is robust enough to remain functional even if dark matter and dark energy do not exist as we currently understand them. If future discoveries show that these entities are not real, the vectors dm and de can be set to 0 or removed. And the remaining parts of the equation will still provide a valid description of the universe. Now, another dichotomy, a thing people frequently talk about being directly in contradiction in a theory. Verbally, they'll argue all day about how this renders the theory non-functional. Light has been instituted as a gravity affecting constant, not a vector. Everything which affects gravity in this equation gets its own vector with space and time coordinates, but not light. Light is represented as both a photon and a wave simultaneously. This is crucial. The dual representation is essential for integrating quantum mechanics with general relativity. Any theory, string theory, loop quantum gravity, that's popularized as a unified theory, when you institute this into the Feynman loops, you will see a lowering of that corrective term. I will include some of that math here. By presenting light in both its particle-like and wave-like properties, the theory incorporates the fundamental nature of light more completely. It's instituted as the most base element of every single component of this equation and framework. The dual representation helps reconcile the probabilistic nature of quantum mechanics with the deterministic nature of general relativity. Light's influence on space-time curvature is inherently included in the equations. This ensures that any interaction involving light, whether at the quantum level or the macroscopic level, is accurately represented and compatible with relativistic calculations. Unified theory's mathematical formalism and quantization are compatible with relativistic calculations. This is achieved through a meticulous embedding, as we discussed, of quantum mechanical calculations into the curvature calculations of general relativity, almost giving us a kind of order of operations here. By ensuring the quantum mechanical probabilities are directly integrated into the geometry of spacetime, the theory maintains internal coherence. This approach helps resolve long-standing discrepancies between quantum mechanics and general relativity. The equation incorporates both scalar and higher dimensional quantities. another dichotomy. Scalars are used for simpler unidirectional properties, while tensors represent more complex multidirectional properties. This distinction is crucial for accurately modeling the diverse interactions within the universe, quantized versus non-quantized, incorporating both quantized, discrete, and non-quantized, continuous. Elements such as this allow the equation to bridge quantum mechanics and classical physics, along with some of the other things we've discussed. We're kind of painting an overall larger picture. For instance, quantum mechanical components like the wave function handle quantized properties, while classical fields like the metric tensor, our good old G underscore ij with the little lowercase g, can be treated as continuous. The theory uniquely integrates quantum mechanics and relativity by using both quantum operators and relativistic tensors, as we discussed. For example, the inclusion of the Einstein tensor with quantum terms ensures that both quantum probabilities and space-time curvature are accounted for, as we've discussed. But it bears repeating. Now that we understand this equation a little more, we're going to look at the principles. I'll put those on the screen here. And we'll kind of go over, again, that diagram of how energy feeds into matter in this model, so to speak. And that'll be shown here too. This kind of gives us an order of operations, so to speak. So, for example, if you were running a calculation with this, you would assume a transformation matrix M acting on space-time coordinates, x, y, z, I, c, t. For the Einstein tensor, you would incorporate dark matter to modify Gij, the Einstein tensor, capital G. For the stress energy tensor, you would modify it with this, and with the dark energy vector. For the metric tensor, or a lowercase gij, would use that to describe space-time separations. That's what that is. And that's a pretty standard form for general relativity, uniquely implemented. For the quantum components, you would calculate these. And of course, you would integrate them into the curvature calculations. And then for acceleration and electromagnetic interaction, you would include these. And of course, you would follow the principles of general relativity and quantum mechanics orders of operations. The more advanced scientists probably know exactly what they are, but for those of us who don't, we can kind of start to form a general understanding here with this. Now, the more advanced people here are probably aware, but I will go over some of just the basic details of what these Feynman loops entail in relation to the experimental results we're going to show you. So, these loops, these Feynman loops, are crucial in quantum field theory as they account for quantum fluctuations too. These loops represent the contribution of virtual particles and are essential for precise predictions of particle interactions. The corrections are categorized into the following categories. And again, what we are doing here is we're looking at string theory, loop quantum gravity, and our own unified theory. We're comparing them in this sense. These loops are a powerful tool to this end. So the corrections of these loops are categorized into a few categories. I can't get into all of them, but I'll go over the major ones relevant to our experimental data. For one loop, that's one run of the mathematical process, is the way I'll phrase that. These are the simplest corrections involving a single loop. Two loop. These are more complex, and they model the interactions between the loops. High order loops. This involves doing multiple loops and provides higher precision. Fractional loops. Now, these aren't used often, but these are fine-tuned corrections and are typically suited for high-order perturbations. So, for string theory, some of the data, to make sense of it, basic quantum corrections at the one-loop level, considered modular invariance and duality. For our two-loop runs, it included interactions between strings and additional particles. For our high-order loops, we made sure that high-order loops. We made sure that it was, meeting the standard of requiring infinity series for accurate predictions. For the normalizability, we ensured that high-order loops have what they require, which is a complex renormalization technique following the principles of string theory. And so each string type has unique characteristics affecting loop corrections in string theory. Every time you run a loop, you have to consider the unique principles of whatever theory you're using, string theory or loop quantum gravity. So this becomes a really powerful tool to compare things in this way. So then for our loop quantum gravity aspect, I just want to detail this for recreatability a little bit. But for the one loop corrections, we accounted for basic quantum gravity corrections involving spin networks. For the two loop corrections, we accounted for interactions with the spin network again, but again, did the same thing as string theory. We included interactions between other loops. And you can start to kind of model those higher order processes. For the fractional loops, we made minor corrections, capturing the finer details of the quantum geometry described by loop quantum gravity. And I'll include the citations. There should be a bunch at the end. I'm going to try to get 100, but I don't know if I'll get near that. For normalizability, we made sure that it, compares with what was found in research on this, which is that it's typically normalizable at low orders. So higher order loops can introduce complexities, and that's an interesting thing. Some things do really good at one loop. That seems to be like the holy grail of ultimate stability for some people. But the high order loops are important too, because they can model those more complex aspects that need to be really researched to kind of balance out the one loop things. And for our unified theory, we know a lot about it. How do we make sure this was instituted and accounted for during our loop corrections? We included corrections accounting for light as both a wave as a particle, the duality, for the one loop. We considered the dynamic nature of dark matter and dark energy. And that was especially in all the vectors. The dynamic nature of all the vectors especially came into play for those two loop calculations. For the high order loops, we made detailed corrections integrating light as both a wave, a particle, dark matter, and dark energy vectors, but then accounting for one loop, two loop, and those interactions simultaneously and modeling those computationally. Not just with normal Python code, but actual quantum computing. And for the normalizability, we designed it to be, the whole equation was designed to be normalizable at low order loops, providing a simplified yet comprehensive approach. So, give me a second here, and we're going to go over some of the experimental results here, the results and analysis. So the results are presented here, and the corresponding bar plot shows loop corrections for 5 different theories, or are data related to this. I don't know what's going to end up in it exactly, but we have tons and tons of data, so I'll put some to this end here. So basically, the plots we're showing kind of illustrate the magnitude of one loop, two loop, harder loops, and fractional loop corrections and kind of compare them for each theory. Here are the string theory values. And for string theory, it's quite interesting. You can do different types of loops. Type 1 loop, type 2 loop, and a heterotic loop. So for string theory, I will show some stuff here about the data for each one of those. The heterotic loops, the type 1 loops and the type 2 loops, and I'll include like a brief description of what that actually entails. For loop quantum gravity, we kind of focused more on just 1 loop, 2 loop, higher order loop, and fractional loops. Those type 1, type 2, and heterotic loops kind of are modeling string interactions in string theory, and that's one of the weird things. For example, each theory you have to account for the nuances. You don't have to necessarily do that with loop quantum gravity. So here are the results there. And then our unified theory. There we go. So this was not only figured out by hand math that was checked by other researchers, including PhDs, private researchers, but also computationally, and then ran through AI, and then ran through me, and ran through my peers again. So this was an intensely rigorous process. It was quadruple mega checked. And if you understand these principles, you can recreate these results directly, and that'll help verify this theory. And the ones we're talking about from other researchers today, and string theory, and loop quantum gravity. So what does this stuff mean? What do all these values and numbers mean? So here's some technical insights. The loop corrections for each theory provide critical insights into their quantum properties. For string theory, all the types, heterotic, type 1, and type 2, we found, supported. These theories exhibit increasing 1-loop corrections from heterotic to type 2, indicating the varying complexity and internal symmetries of the system. High-order loop corrections are relatively small, but essential for accurate predictions. For loop quantum gravity and unified theory, we're going to go over this in a second, but we found out some amazing things about how they're pretty much, the corrective terms are exactly pretty much the same. And we'll go over that, but we found out that they share some very similar properties which make them functional, supporting what I said earlier, that there is a range of unified theories which follow similar principles, but have a range of uses and personal development which may have affected their form. So, for loop quantum gravity and unified theory, our unified theory that we're going over here, the main one here, both theories yielded nearly identical corrections, suggesting they share fundamental principles in quantizing spacetime, which we did figure out, so we'll go over that in a little bit. The small differences in high order and fractional loop corrections highlight subtle distinctions in their approaches to integrating quantum mechanics with general relativity. Now, one more time, I think it's important to go over some of the broad implications of this in lay people terms and expert terms. So for experts, the results validate the theoretical constructs by showing consistency and precision in the quantum corrections. They help identify which theories align better with the principles of quantum gravity and unification. And for the non-experts, this analysis is like comparing detailed sketches to see which one best matches the real landscape, as we spoke about. It helps us understand how different theories adjust their predictions to align with observed data, thus extending the vision of our eyes. Now, if you want to do recreatability or test this for the more advanced scientists out there, you can do renormalization group flow analysis and study how the parameters evolve with energy scales. That will confirm what I'm saying as well. Monte Carlo simulations use stochastic methods to stimulate and analyze more complex interactions. Anomaly cancellation. Investigate the cancellation of anomalies in different theories to ensure mathematical consistency here, especially in regard to the three we're talking about. For phenomenological model comparisons, you can compare the theoretical predictions with experimental data from particle accelerators. We do that, so you probably don't have to. You can probably expand on that later. And for the non-perturbative effects, that's a hard one, explore non-perturbative corrections that might affect the loop correction calculations, providing deeper insights into the theory's robustness. I really do hope that as many scientists and mathematicians as possible pause this, pick it apart, verify it if they can. It is in a way self-authenticating, but in a way Peer review is very important, but it doesn't supersede data. So I'm very curious to see, and I would challenge anyone, if they're out there, to check this stuff out. So now we're going to go over a little bit of the weirdness I figured out with some of the similarities between loop quantum gravity and our unified theory here. So we'll detail that, and then we'll get on to the Higgs boson data, the Reimann solution data, verifying a few other people's kind of emerging unified theories, doctors and researchers, and then we'll be done. We'll detail how to use this right away, how to utilize it for personal benefit, start advancing any type of research or development that you would like.
Hello, so we're now going to go over the experimental results of matching our data to the Higgs boson data with this unified theory, and also our Reimann solution paper, which is under peer review. And even better, we had recently a PhD reach out to me, and I wrote a paper with him about his elaborations on how that can be useful for physics. So I wanted to go over that a little bit here. We found some pretty astonishing things. We found we could fully extract the properties of the Higgs boson independently of having any of that data, just from the framework itself. So that was amazing. And there's a lot of other things that we're going to go over quick, but we don't have much time, so I will be kind of just sorry if I'm maintaining my worst eye contact so far in this whole presentation, because this is a lot of highly technical information, and I just want to make sure I go through it as fast as possible. So start here. So the solution to the Reimann hypothesis we have presented in our research document uniquely leverages elements from quantum mechanics and general relativity by treating these physical theories as mathematical frameworks. Specifically, quantum mechanical operators such as the Hamiltonian were used to model the energy levels corresponding to the non-trivial zeros of the Reimann zeta function. These zeros are analogized to quantum states, with their distribution and characteristics analyzed through the lens of quantum mechanics. In parallel, general relativity's tensor formalism, particularly the stress energy tensor, was adapted to refine the growth conditions of the zeta function within the critical strip. Adjustments to this tensor included contributions analogous to dark matter and dark energy in the equation, highlighting the potential influence of these components in the mathematical formulation. These tensors were not used for their physical interpretations, but for their inherent mathematical properties, providing a structured approach to explore and validate the critical line hypothesis. And so by integrating these two advanced fields, the approach not only confirmed the theoretical placement of the zeta function's non-trivial zeros on the critical line, but also introduced a novel interdisciplinary method where strictly mathematical aspects of physics-based theories were harnessed to solve a profound problem in pure mathematics. This method illustrates the deep and often surprising connections between how different domains of science, showcasing advanced theoretical frameworks, can transcend their original context and address foundational problems in mathematics. And then beyond that, the paper that was written to elaborate on this and support the work, which is also under peer review, is from Dr. Saeed Kazim Musavi and me. We wrote that. And that was a really interesting physics application immediately. I got really good response from a lot of people right away. Summary of that paper here. This paper explores the relationship between the Reimann hypothesis and a six-dimensional spacetime model, suggesting that the critical line zeros correspond to physical phenomena in a six-dimensional framework. The theory integrates quantum mechanics and general relativity, providing a potential unified theory. The work proposes a new perspective on the Reimann hypothesis by connecting mathematical structures with physical theories, potentially bridging gaps between physics and mathematics. So both documents emphasize the integration of quantum mechanics and general relativity into the mathematical framework of the Reimann hypothesis. The unique contribution lies in leveraging these physical theories for their mathematical properties rather than physical interpretations. This interdisciplinary approach offers novel insights and methods for proving complex mathematical conjectures, such as the Reimann hypothesis. And so what we essentially did here is we instituted a little bit of his work, and then the original document, and we came up with some really crazy computational processes that really elucidated how we could derive Higgs boson data and characteristics independent of having that data and then compare it. So I have like a bunch of citations here for those characteristics of the Higgs boson and how they were matched up. That's also in the CERN data and all their repository data. Excuse me. And one thing I would like to say as well is I'm going to go over really quick for that theory that we were just talking about. There is, it's composed of a series of lemmas, theories, and theorems. So we're going to go over those right now. Lemma 1, entire function of order 1. The Reimann zeta function is classified as an entire function of order 1, indicating that its growth rate is controlled and can be extended to the entire complex plane, barring a simple fault. Theorem, and then 2. Theorem 1, non-trivial zeros on the critical line. This theorem asserts that all non-trivial zeros of the Reimann zeta function are located on the critical line, where the real part of the complex number is half. This statement is central to the proof of the Reimann hypothesis. 3. Functional equation symmetry. The Reimann zeta function satisfies a functional equation that demonstrates symmetry about the critical line. This property is crucial for analyzing the distribution of zeros. The zeta function can be represented as an infinite product over prime numbers, establishing a deep connection between the zeta function and the distribution of prime numbers. 5. The argument principle. This principle in complex analysis relates the number of zeros and poles of a meromorphic function to the change in the argument of the function along a closed contour. It is used to calculate the number of zeros within specific regions, supporting the hypothesis that they lie on the critical line. Quantum and general relativity refinements. Elements from quantum mechanics and general relativity, specifically operators and tensors, are incorporated to refine the theoretical framework and improve the accuracy of numerical verification. These refinements are applied strictly for their mathematical properties rather than their physical interpretations. 7. Modified stress energy tensor. The document discusses the modification of the stress energy tensor to include contributions from dark matter and dark energy, scaled by specific coefficients. This adjustment helps refine the behavior of the zeta function within the critical strip, further supporting the proof. So, using advanced computational mathematics techniques and our unified theory framework, we can model and predict particle behaviors without direct experimental data, like that obtained from the Large Hadron Collider. This approach not only validates known data, but also provides a powerful tool for discovering new particles and interactions, potentially reducing the need for expensive and complex physical experiments. We were able to do some pretty amazing things here. We were able to literally simulate and model 100 particle interactions with the Higgs boson at once, using nonlinear classical computing by just instituting this unified theory. And it's really amazing because it kind of condenses down the amount of calculations and computation needing to be done. You might need to have multiple imports, multiple methods of calculation. You might even need a quantum computer. But this kind of is able to do all of that in one equation, which really reduces the computational requirements a lot, because it was really great. And simulating 100 particles with detailed properties such as mass, decay rate, and coupling constants using classical computation, especially within the framework of a nonlinear unifying theory, represents a huge achievement for us. Typically, such detailed simulations would require the parallel processing capabilities of quantum computers due to the exponential growth of state spaces and interactions. So, I'm going to go over a little bit about how we did this here. And I will write a document about this probably with Dr. Musabi. Let's go over this process here, and I'll show some stuff on the screen to kind of help a general understanding of the process we use mathematically. I had to do a weird editing cut here because I realized I should detail this iterative process we use for the computational mathematics because it's very interesting. So, really quick, we'll go over this. objective. The goal was to adjust the parameters with the theoretical unified theory model, specifically within this framework, and sit in the six-dimensional space-time model, to match the observed experimental data, Higgs boson, and decay rates as closely as possible. We set the initial conditions and assumptions, the self-coupling constant and the matrix elements for decay processes. We set the vacuum expectation value. We set the target observables, which are the Higgs boson mass and the total decay rate, and the branching rates for specific decay channels. So the steps in this iterative process during the math were to start with the initial values for the parameters and based on theoretical considerations and previous studies. 2. To calculate the observables, to calculate the Higgs mass, total decay rate, and branching ratios for various decay channels using the initial parameter values. We computed the error between the calculated observables and the experimental data. The error function could be defined as this. So we adjusted the parameters to reduce the error. This refinement can be guided by numerical optimization techniques such as gradient descent or other suitable algorithms. After each iteration, we checked if the error is below a predefined tolerance level or if the change in error is negligible. If the convergence criteria are met, then the iteration just stops, and that's a good computational process we've been using. That's a good way to utilize these unified theories when you are performing computation. Then you just repeat, if convergence criteria are not met, you just repeat the process from step 2 in parameters. And then you recalculate the observables and find the error function. We use gradient descent too, which is pretty cool. It's a method to minimize the error function by iteratively moving in the direction of the steepest descent mathematically. And that's calculated from the gradient of the error with respect to the parameters. So we did literally 1,000 iterations of this manually. And after doing that 1,000 times, the parameters were adjusted to a point where the Higgs boson mass and decay rates were pretty close to experimental values. But we went beyond that and did 10,000 manually. It was ridiculously painstaking. We extended the process to 1,000 iterations and provided a further fine-tuning of the parameters, reducing the error even further and achieving a highly accurate match with the experimental data. We ensured that the adjustments did not lead to numerical instability. We balanced the accuracy of the solution, the computational resources, and time. We ensured that the parameters converged to values that were precise, with low variance and accurate and closer to true values. And this iterative refinement process allowed for the fine-tuning of the theoretical model parameters in this context, and that resulted in predictions that were consistent with actual Higgs boson data. So basically we circumvented, I see it that way, it might not be correct, but I feel like we circumvented having a Large Hadron Collider, and that's cool. And we did match that up against the data from CERN repositories. So, yeah, on to the little next part about the math now. So to kind of explain this process a little bit, to incorporate Dr. Saeed's six-dimensional space-time utilization of our Reimann solution, we use the six-dimensional space-time framework to model particle interactions, employing higher dimensional geometry and tensors. This framework provides additional degrees of freedom, allowing for richer description of fundamental interactions, particularly the coupling constants and masses of particles. And then we integrated quantum mechanics and general relativity based off of the unified theory. And the integration involved quantum mechanical operators, such as the Hamiltonian for energy eigenvalues and general relativity tensors like the stress energy tensor to describe complex particle properties and interactions. This dual framework allows for a coherent description of gravitational and quantum effects. And then we incorporated the Reimann solution, so it's kind of a three, his document, the Reimann solution, and then the unified theory, and that document, the one we've been going over here today. So as for the Reimann Hypothesis incorporation, the zeros of the Reimann zeta function were used as a mathematical tool to refine theoretical predictions. Specifically, the distribution of these zeros helped in fine-tuning the eigenvalues associated with the Higgs field potential and decay rates. And we were able to extract these from the unified theory itself, and that's pretty amazing. and it matches up perfectly with the actual characteristics. So we used the Higgs potential function and calculated the Higgs boson mass with parameters where we set the self-coupling constant and the vacuum expectation value. The second step had to do with the decay rates and branching ratios. So a decay width was set and calculated where this right here denoted the amplitude of decay process, adjusted, and we adjusted that based off of the unified theory interaction terms. The theoretical decay rate closely matched the observed decay rate. But we're focusing on decay rate and mass because we're still working on iterating the other ones in the computational processes. So 3, coupling constants and interaction strengths. Coupling constants were recalculated by integrating 6-dimensional metric tensors with known standard model interactions. This included refining the couplings for particles such as the top quark and WZ bosons. The application of the Reimann function zeros helped refine eigenvalues associated with the Higgs potential and the decay rate properties. This mathematical framework provided a unique approach to validating theoretical predictions. After extensive iterative calculations and adjustments, we got these values. And honestly, that's quite amazing. For the mass, we got 125.09 independently. The actual value generally given is 125.10. So that's an incredibly good margin of error. And I'll show the decay rate too up here. And that's just amazing. Some of these graphs have hundreds of thousands of points. We were able to perform nonlinear computing so well. We got up to probably 70% of the efficiency of a quantum computer, and that's pretty amazing. I wanted to not use actual quantum computing for this one because I was trying to investigate how powerful these things could be instituted together without that. All of the other graphs in this presentation in some way incorporated quantum computing, but I didn't want to do it with this. I wanted to extract these values from scratch, and what this does is it kind of does two things. It attaches mathematics to our unified theory and our general conversation here today, but it also immediately shows the benefit in the use. Not only was I able to institute this theory to publish that Reimann solution paper, but another PhD was able to build on it in a way where I then built on it again to extract these values. I worked with him and a couple other people, and the mathematics coming out, the graphs especially, are beyond amazing. And I'm showing some of those here, but geometrically pleasing and mesmerizing, and this shows immediately the benefit and use of understanding a theory such as this. So before I go, I was going to create a long section about AI and AI prompts and how to utilize these theories immediately. I think I've demonstrated that pretty well, and I've gone over the time here today because it's just such a complex topic, and I wanted to make sure it was fully understood. But I can say before I go, if the number one thing that I would do, take this to AI, give it the research document for this theory or any related theories. I'll list some here. These are the theories that I know have low loop correction abilities, like 1 loop or less, Feynman loop, and other associated properties which are either promising or being investigated or have been verified. So take these theories, find unique ways to utilize what you learned here today, and not only use your own brain and mind to come up with these ideas, but iterate them with the artificial intelligence, give them these theories, and then say, if you want to create a blueprint, say, all right, now that you have this theory, I want to use this theory to model 4-dimensional space-time for a gravity manipulation device or a propulsion system. You can calculate a propulsion system at multiple points while accounting for tons of different engineering details and how they weight and interplay with each other. And the good thing is it's not magic. This is kind of self-limiting, because if you don't have the skill set to drive that iterative process, then it's null. So that's why I think this presentation is important. I was going to give a lot more information about the AI side of it, but with the foundational understanding of the things here, I think it's easier and easier to take these ideas and utilize AI to help advance things like alternative propulsion or, you know, alternative energy. I'll include a cool little plot here from a project recently where we were able to calculate actual electromagnetic field alterations from a device, and we use this Unified Theory Institute in code to do this. These nonlinear computing capabilities are vastly important, and near quantum computing should be looked into more, especially in the form of unified theories. And I think today, now that we've gone over these things and some of the experimental results, I'd just like to say that I hope you guys use this information for the betterment of society and science, and just share it with everyone you know. So I'm glad you were here today, and I've had a good time. Thank you.
Oh, I can't hear you.
Sorry, I was muted. So let's do this. We do not have a lot of time because I have to bring Gerald in for a quick presentation also. So what I'm going to do is bring everybody in. Why don't we do this? Why don't we give you an enormous applause, sir, for Mr.
Thank you.
Alex Wolf.
Thank you.
There. See, we're getting the gang
You all
back.
did great. I enjoyed that last presentation. I shared some information there in the chat. I hope it helps some people.
Yeah, no, that was a knockdown, drag out,
interested.
man. Thank you. Thank you for the enormous presentation. Thank you for going through all the unified theories and all that stuff.
And I would like to say, small little company I work for, if anybody wants to ever exchange ideas or technology, we're open to that. These ideas were all developed within that company, WTRC. So I would mention that. And it was hard. It took forever. The iterations took forever. I really did those manually. It wasn't like each calculation did it 11,000 times. And so I kind of went crazy. But I think it turned out good. I got some cool graphs out of it. So.
Okay, so, sir, let me thank you so much. And again, normally we do like a lengthy Q&A, but I need to have things wrapped up. Yeah, by 6 p.m.
Would you like me to reschedule there, Tim, so that we can do this another time, or?
Well, I mean, Gerald, you were going to share your video, right? You were going to share the video.
Yeah, but it's okay. I can do this next time if you'd like.
Do you want to do that? Well, if you want to do that, let's go right into Q&A then. Let's go right into Q&A. Okay. And my little studio here, I have no air conditioning.
I would love to hear it if you have, you know.
Gerald, just play your video at least.
Gerald, do you want to put the video up? Put the video up and we'll reschedule for next time.
Well, see, that's the thing. It's a bunch of different videos, and then I was going to do a live presentation, a live experiment, but because of the way that the whole thing is going to work, it'd probably be better if we did it next time. Let everybody hang on the edge of the fence for what they're going to see on the next round.
I'll definitely watch. I want to see it. So I'll definitely be there, at least to watch. Okay. I probably won't present anything, and then yeah.
Awesome. Well, let's do that then. Alex, thank you again, man. Thank you again. That was I had no idea. I mean, that was a long, detailed. You went through every aspect of that. So thank you so much.
Thanks. Yeah.
Okay.
I hope, and I would say because just a 10-second thing here. Anybody IP theft has been rampant in the community lately. Don't do that. That presentation can teach you how to just build your own theory, and that's what I'd recommend. That's what I'm.
Okay.
That was the whole point. Thank you.
Well, thank you, man. So, guys, let's put our hands together one more time for Alex Wolf. Alex, thank you again, man. Thank you. And let's go into lab time if we can. We'll probably do about an hour with that, and then try and wrap things up. Okay. And I think we have everybody on here who's on with us. So yeah, in lab time. So Mark, are you still there?
I think he said he was on the road, but I'm not sure.
Okay. I mean, what we could do is wrap things up a little early if no one has. So I'm traveling tomorrow, so that's part of it. I'm trying to kind of get prepped and packed and all that stuff.
Gotcha. Fair enough.
Well, why don't we do that then? Why don't we call this one a little bit early? We'll make this one a little bit shorter. And so why don't I will thank everybody who participated in tonight's event. So I will put timestamps into this as well. And we have more coming up too. I mean, like I have people scheduled out to infinity at this point. It's insane, but it's all good. So, okay. Well, let's do that. So I guess this has been APEC for Saturday, August 3rd, 2024. So thank you, guys. Thank everyone.
Thank you. All right.